Welcome, we're so happy you tuned in tonight. Before we get started, I'd love to know, where are you watching from? Drop it in the comments. Now, let's get comfortable and drift into deep, peaceful sleep together. The night sky holds a gentle secret that appears most often near the poles of our planet. If you were standing in the dark expanse of northern Alaska on a clear winter evening, or perhaps on the windswept coast of Norway, you might look up and see something that seems almost impossible. Curtains of light flowing across the darkness, glowing in shades of green and sometimes red or purple, moving slowly like fabric caught in an invisible breeze. These are auroras, natural light displays that happen in Earth's upper atmosphere, and they are among the most beautiful phenomena our planet has to offer. The lights you would see in the north are called Aurora Borealis, a name that comes from Aurora, the Roman goddess of dawn, and Boreas, the Greek god of the north wind. In the southern hemisphere, the same phenomenon occurs and is called Aurora Australis, with Australis simply meaning southern. Both are the same kind of event, just happening at opposite ends of the Earth, and both are part of a quiet, ongoing conversation between our planet and the sun. To understand what an aurora truly is, we need to think about what happens high above us, far beyond where airplanes fly, far beyond where weather occurs, in a region of the atmosphere so high and so thin that most people never think about it at all. Auroras happen when energetic particles from space enter the region near Earth's poles and interact with the gases in our upper atmosphere. Most of those particles come from the sun, travelling across the vast emptiness of space for days before they arrive at Earth. When they get here, Earth's magnetic field, an invisible shield that surrounds our planet, guides these particles toward the polar regions, funneling them downward along curved pathways that dip toward the surface near the Arctic and Antarctic. The light you see during an aurora appears when these fast-moving particles collide with atmospheric gases like oxygen and nitrogen. Those collisions excite the atoms and molecules, which is a way of saying the particles transfer some of their energy to the gases, like gently charging them up. When the gases relax back down to their normal state, they release that extra energy as light, and that light is what we see as an aurora. It's a process that happens continuously, high above the clouds, invisible during the day, but revealed in all its quiet beauty when the sun sets and darkness falls. Auroras are most common in a ring-shaped zone around each pole called the auroral oval. This oval isn't a perfect circle, and it doesn't sit exactly at the geographic pole. Instead, it's centered around the magnetic pole, which is offset from the true north and south poles by several degrees. The auroral oval shifts and changes size depending on how active the sun is and how much energy is flowing into Earth's magnetosphere. But on average, it forms a band that passes over places like northern Scandinavia, Iceland, Alaska, northern Canada and Siberia in the north, and over Antarctica, and occasionally the southern tips of New Zealand and Tasmania in the south. If you live within or near this oval, you have a much better chance of seeing auroras on any given night. If you live farther away, toward the equator, auroras are rare, though during particularly strong geomagnetic storms, the oval can expand and push the lights farther south or north than usual, sometimes bringing them within view of places that almost never see them. Auroras are easier to see at high latitudes, which simply means the farther north or south you go, the more likely you are to witness them. In the northern hemisphere, they often appear in Alaska, northern Canada, Iceland, Norway, Sweden and Finland. These regions fall within or close to the auroral oval, and during periods of higher solar activity, auroras can be a regular sight, appearing several times a week or even multiple times in a single night. In the southern hemisphere, the situation is a bit different, because there's less populated land at high latitudes. Antarctica is the prime location, but because few people live there, most southern aurora sightings come from places like southern New Zealand, Tasmania, and occasionally the southern tips of South America and South Africa during strong auroral events. The southern lights are just as beautiful as the northern ones, but they're seen by far fewer people simply because there are fewer people living in those remote areas. One thing that surprises many people is that auroras don't happen at ground level. They're not like fog or clouds that you can walk through or touch. Auroras glow high above the surface, suspended in the upper atmosphere like a luminous painting that hangs in the sky. The typical altitude where auroras begin to appear is around 80 to 100 kilometers up. To put that in perspective, commercial airplanes fly at about 10 to 12 kilometers, and even the highest clouds, the wispy cirrus clouds, only reach about 10 to 15 kilometers, auroras start much higher, well into the region called the thermosphere, where the air is so thin that it would feel like a near vacuum if you could somehow be transported there. Some auroras can reach even higher, extending up to several hundred kilometers above the surface. The exact altitude depends on the energy of the incoming particles and the type of gas they're colliding with. But the point is that auroras are a high-altitude phenomenon, something that happens in a part of the atmosphere most of us never interact with in our daily lives. The reason auroras are concentrated near the poles has to do with Earth's magnetic field. The magnetic field is generated deep inside the planet by the motion of molten iron in the outer core, and it extends far out into space, creating a protective bubble around Earth called the magnetosphere. The field lines of this magnetic field loop out from the southern hemisphere, arc through space, and come back down in the northern hemisphere. Near the equator, these field lines are nearly horizontal, running parallel to the surface, but near the poles, they dip steeply downward, pointing almost straight into the Earth. These downward-pointing field lines act like invisible pathways for charged particles. When particles from the Sun encounter Earth's magnetosphere, they get caught up in the magnetic field and are guided along these field lines. Because the field lines converge near the poles, the particles are funneled downward into the upper atmosphere in those regions, where they collide with gases and create the glowing displays we call auroras. The poles are special not because they're colder or darker, but because the geometry of Earth's magnetic field naturally directs energetic particles there. The auroral oval itself is not a fixed ring. It expands and contracts depending on how much energy is being delivered to Earth's magnetosphere by the solar wind. During periods of low solar activity, the oval is smaller and sits closer to the magnetic poles. During stronger solar activity, when more particles are streaming toward Earth, or when a particularly energetic burst of solar material arrives, the oval expands, sometimes dramatically. This is why, during big geomagnetic storms, auroras can be seen much farther from the poles than usual. People in places like Scotland, northern parts of the United States, or even farther south have occasionally witnessed auroras during these intense events. The expansion of the auroral oval is a direct response to increased energy input from the Sun, and it's one of the ways scientists can tell when a geomagnetic storm is underway. Now, let's talk about the colours, because the colours of an aurora are one of the most striking things about them, and they're also a direct result of the physics happening in the upper atmosphere. Green is by far the most common aurora colour. If you were to look at 100 different auroras, the vast majority would feature green as their dominant hue. This green light often comes from excited oxygen atoms. When a fast-moving particle from the Sun collides with an oxygen atom in the thermosphere, it can knock one of the atom's electrons into a higher energy level. The electron doesn't stay there for long, it quickly falls back down to its normal state, and when it does, it releases the extra energy as a photon of light. For oxygen atoms at certain altitudes, that photon happens to be green, with a wavelength around 557.7 nanometers, which is right in the middle of the visible spectrum and very close to the wavelength our eyes are most sensitive to. Green auroras frequently glow at altitudes around 100 to 150 kilometers, where the atmospheric density is just right for this process to dominate. Red auroras are also caused by oxygen, but they tend to appear at higher altitudes, usually above 200 kilometers. At these greater heights, the air is even thinner, and the collisions between particles and oxygen atoms happen less frequently. This gives the oxygen atoms more time to relax from their excited state, and under these conditions they emit red light instead of green. Red auroras are less common than green ones, partly because they require specific conditions and partly because they're often fainter and harder to see. When they do appear, they can add a stunning layer to the display, sometimes forming a red glow above the green curtains, creating a layered effect that looks almost like a watercolour painting spread across the sky. Blue and purple tones in auroras often involve nitrogen. Nitrogen makes up about 78% of Earth's atmosphere, so it's abundant even at high altitudes, and when charged particles collide with nitrogen molecules, they can produce blue and purple light. Lower altitude auroras, those happening closer to 80 or 90 kilometers up, tend to show more purples and blues because that's where nitrogen is relatively more dense. The exact shade depends on whether the nitrogen is in its molecular form or has been broken apart into individual atoms, and on how much energy the incoming particles are carrying. Sometimes you'll see a mix of blue at the bottom edge of an aurora with green higher up and red higher still, creating a spectrum of colours that reflects the changing composition and density of the atmosphere with altitude. The colour of an aurora depends on two main things: which gas is glowing and at what altitude the collisions are occurring. It also depends on how much energy the incoming particles carry. Higher energy particles can penetrate deeper into the atmosphere before they lose their energy through collisions, so they tend to create lower altitude auroras with more blues and purples. Lower energy particles are stopped higher up, where they produce greens and reds from oxygen. Many auroras are a blend of colours layered by altitude, like soft curtains hanging in the sky. From the ground you might see green at the base, fading to red at the top, with hints of purple or blue at the edges. It's a natural spectrum created by the chemistry and physics of the atmosphere, and it changes moment by moment as conditions shift. Auroras don't just appear as shapeless blobs of light, they take on distinct forms and structures that can change over the course of a display, sometimes slowly, sometimes quickly. Many auroras begin as calm arcs across the sky, smooth bands of light that stretch from one side of the horizon to the other, often running roughly east to west. These arcs can be quite faint at first, barely visible, like a faint glow just above the northern or southern horizon. As the aurora strengthens, the arc might brighten and begin to develop structure. It can form tall curtains that ripple and fold like fabric hanging in the air. These curtains can wave gently, their lower edges sharp and their tops fading into darkness, and they can extend vertically for hundreds of kilometres, though they always remain high above the ground. Some auroras appear as bands that stretch from horizon to horizon, and within those bands you might see fine vertical stripes called rays. These rays align with Earth's magnetic field lines, and they give the aurora a striated appearance, like columns of light extending upward. The rays can be quite narrow, just a few hundred meters across, and they can move and shift as the magnetic field and particle flows change. When an aurora is directly overhead, it can form a shape called a corona, where the rays seem to spread outward from a central point, like the spokes of a wheel or the petals of a flower. This is actually an optical effect caused by perspective. The rays are still aligned with the magnetic field, but because you're looking up at them from below, they appear to radiate outward. It's one of the most dramatic forms an aurora can take, and it's a sign that you're standing right under the auroral oval. The motion of auroras is one of their most mesmerizing qualities. They're not static. They brighten and dim in pulses, they drift across the sky, they ripple and wave. This motion comes from changes in the flow of particles and the conditions in the magnetosphere. Sometimes the aurora moves slowly, drifting gently from one part of the sky to another, over the course of minutes or hours. Other times it can dance quickly, with curtains flaring up, brightening, and then fading in just seconds. The speed of the motion doesn't mean the light itself is moving that fast. Remember, the glow is happening far above the clouds, and what you're seeing is the result of changing conditions in the upper atmosphere and magnetosphere. It's like watching a spotlight play across a distant surface. The light itself doesn't move, but the pattern it creates does. Even when auroras look like they're moving fast, it's important to remember that the glow is still, happening far above us. The curtains and arcs are not rushing through the air like a storm. They're the result of regions of the upper atmosphere being excited by incoming particles, and as those regions shift and change, the glow shifts with them. It's a dynamic process, constantly responding to variations in the solar wind and the magnetosphere, and that's what gives auroras their living, breathing quality. They can brighten and dim in pulses, almost like they're breathing, and they can develop sudden bright patches called auroral substorms, where a relatively calm aurora suddenly erupts into a brighter, more active display. These substorms are caused by the release of energy that is built up in Earth's magnetotail, and they can make the aurora much more dramatic for a short period, usually lasting from a few minutes to an hour or so. To really understand auroras, we need to talk about the sun's role, because without the sun there would be no auroras on Earth. The sun is not a static ball of light in the sky. It's an incredibly active, dynamic star, constantly churning and roiling with nuclear reactions in its core and complex magnetic activity in its outer layers. The sun continuously releases a stream of particles called the solar wind. This wind is made up mostly of electrons and protons, and it flows outward from the sun in all directions, filling the solar system. The solar wind carries with it the sun's magnetic field, stretching it out into space like a web that permeates the entire region around the sun. The speed of the solar wind varies, but it typically travels at about 400 kilometers per second, though it can be faster or slower depending on conditions on the sun. Auroras get stronger when solar wind conditions are more intense. If the solar wind is blowing harder, carrying more particles and more energy, then more of those particles can interact with Earth's magnetosphere, and more energy can be transferred into the upper atmosphere, creating brighter and more active auroras. But the solar wind is not the only factor. Sometimes the sun releases sudden, dramatic bursts of material and energy. One of these is called a coronal mass ejection, or CME. A CME is an enormous eruption of plasma and magnetic field from the sun's corona, the outermost part of its atmosphere. When a CME is directed toward Earth, it can send billions of tons of solar material hurtling through space toward us. When this material arrives, usually 1 to 3 days after the eruption, it can trigger a geomagnetic storm, compressing Earth's magnetosphere and injecting large amounts of energy into it. This can cause the auroral oval to expand dramatically, bringing auroras to latitudes much farther from the poles than usual, and making the displays much brighter and more active. Solar flares are another type of solar activity that can affect auroras. A solar flare is a sudden, intense burst of energy from the sun's surface caused by the rearrangement of magnetic fields in the sun's atmosphere. Flares release energy across the electromagnetic spectrum, from radio waves to X-rays, and they can also accelerate particles to very high speeds. If the flare is associated with a CME, the combined effect can be particularly strong. Not all flares lead to enhanced auroras, though. It depends on whether the particles and energy are directed toward Earth, and whether the magnetic fields in the solar wind align in a way that allows them to couple efficiently with Earth's magnetosphere. Coronal holes are another feature of the sun that can influence auroras. A coronal hole is a region of the sun's atmosphere where the magnetic field is open, allowing solar wind to escape more easily. These regions appear dark in certain wavelengths of light, because they're cooler and less dense than the surrounding areas. When a coronal hole is facing Earth, the fast solar wind streaming from it can enhance aurora activity when it reaches our planet. These high-speed streams are more persistent than CMEs, often lasting for several days as the sun rotates and the coronal hole sweeps past Earth like a cosmic lighthouse beam. All of this solar activity, the solar wind, CMEs, flares and coronal holes, is part of the sun's normal behaviour. The sun goes through cycles of activity, with periods of higher and lower activity following a roughly 11-year pattern called the solar cycle. During solar maximum, when the sun is most active, there are more sunspots, more flares, more CMEs, and generally more auroras on Earth. During solar minimum, activity is lower, and auroras are less frequent and less intense, though they still occur. Space weather is the term scientists use to describe these changing conditions in the solar wind and the near-Earth environment, and just like weather on the ground, it's always changing. But unlike terrestrial weather, space weather is driven by events happening 93 million miles away on the sun, and it affects the invisible magnetic and particle environment around our planet rather than the air we breathe. You can think of auroras as Earth's gentle response to the sun's outgoing flow. The sun is constantly shedding material and energy, and when that material reaches Earth, our planet's magnetic field responds by guiding some of it toward the poles and converting it into light. It's a process that's been happening for as long as Earth has had a magnetic field and an atmosphere, which is to say for billions of years. The aurora you see on any given night is part of a continuous conversation between our planet and its star, a reminder that we live in a solar system, not in isolation, and that the space between Earth and the sun is not empty, but filled with particles and fields and activity. Earth's magnetic field plays a crucial role in creating auroras, and to understand how, we need to think about the structure of this field and how it interacts with the solar wind. The magnetic bubble that surrounds Earth is called the magnetosphere. It's not a physical structure. It's a region where Earth's magnetic field is strong enough to dominate the behaviour of charged particles. The magnetosphere extends tens of thousands of kilometres into space, and it acts as a shield, deflecting many of the charged particles from the solar wind away from Earth. Without it, those particles would stream directly toward the surface, where they could damage the atmosphere and potentially harm life. The magnetosphere is constantly being buffeted and shaped by the solar wind, which is why it doesn't have a simple, symmetrical shape. On the side of Earth facing the Sun, the magnetosphere is compressed by the pressure of the solar wind. The boundary between the magnetosphere and the solar wind, called the magnetopause, can be pushed inward to within about 10 Earth radii on the day side. On the night side of Earth, away from the Sun, the magnetosphere is stretched out into a long tail called the magnetotail. This tail can extend for millions of kilometers downstream, far beyond the Moon's orbit. The magnetotail is not just an empty extension of the magnetic field. It's a region where energy can build up, stored in the stretched and stressed magnetic field lines. When conditions are right, this energy can be released suddenly in a process related to magnetic reconnection. Magnetic reconnection is a fundamental process in plasma physics, and it plays a key role in creating auroras. It happens when magnetic field lines that are pointing in opposite directions come close together and suddenly snap and reconnect in a new configuration. When this happens, it releases a large amount of stored magnetic energy very quickly, and that energy can go into accelerating charged particles to high speeds. In the magnetotail, reconnection can cause field lines to snap back toward Earth, flinging particles earthward along the field lines. Those particles then follow the field lines down into the upper atmosphere near the poles, where they collide with gases and create auroras. This is why auroras can suddenly brighten or become more active. It's often a sign that a reconnection event has occurred in the magnetotail, releasing energy and sending a fresh batch of particles streaming toward the atmosphere. Auroras are, in a sense, one visible sign that the magnetosphere is active and protective. The same processes that create the beautiful lights in the sky are also processes that prevent harmful radiation and particles from reaching the surface. The magnetosphere is constantly interacting with the solar wind, absorbing energy, deflecting particles, and occasionally releasing that energy in bursts that light up the polar skies. It's a dynamic, ever-changing system, and auroras are just one of the many ways we can observe its activity from the ground. One common question people have about auroras is why we typically see them at night. The answer is simple. Auroras actually occur during the daytime as well, but sunlight makes them impossible to see. The glow of an aurora, even a bright one, is faint compared to the scattered sunlight that fills the sky during the day. When the sun is up, the entire sky is illuminated, and the relatively dim glow of the aurora is completely washed out. It's only when the sun sets and darkness falls that your eyes can pick up the faint light of the aurora against the dark background of the night sky. Darkness helps your eyes become more sensitive, and it reveals the subtle glows and colours that would otherwise be invisible. Clear skies are essential for seeing auroras. Clouds block your view of the upper atmosphere just as they block your view of stars and planets. If there's a thick layer of clouds between you and the aurora, you won't see it, no matter how bright it is. This is why aurora watchers always check the weather forecast, hoping for clear conditions. Low light pollution also makes a big difference. In a city with bright streetlights and buildings, the sky glow can make it hard to see faint auroras. Out in the countryside, far from artificial lights, even a relatively weak aurora can be quite visible. The contrast between the dark sky and the glowing aurora is much greater when there's no competing light pollution. Auroras can be dim and still beautiful. Not every aurora is a bright, dramatic display that fills the sky with vivid colours. Some are faint and subtle, like a pale watercolour wash across the northern or southern horizon. These faint auroras are still the same phenomenon, they're just the result of less energetic conditions in the magnetosphere. Even a dim aurora is worth watching though, because it can change. A faint arc can suddenly brighten, or it can develop structure, or it can slowly fade away. There's a quiet beauty in watching the sky and seeing these subtle changes unfold. The brightness of the moon can also affect aurora visibility. A full moon is bright enough to illuminate the landscape and create a significant amount of sky glow, which can reduce the visibility of faint auroras. Many aurora photographers prefer nights with little or no moonlight because it allows the aurora to stand out more clearly. However, a bright moon can also be helpful because it illuminates the foreground, allowing you to see the landscape as well as the aurora, which can make for beautiful photographs with both the aurora and the surrounding environment visible. Winter often provides the best aurora watching conditions, especially at high latitudes, and the reason is straightforward. Nights are longer. In the Arctic and Antarctic during winter, the night can last for many hours, or in some places near the poles for weeks or even months. This extended darkness gives you more time to observe auroras and increases the chances that you'll be looking at the sky when an aurora appears. Summer, on the other hand, can have very short nights or none at all in the far north or south, making aurora viewing difficult or impossible simply because it never gets dark enough. The aurora is still happening, but you can't see it against the bright twilight sky. Auroras are frequently seen around local midnight, but they can appear at any time during the night. The exact timing depends on many factors, including your location relative to the auroral oval, the level of geomagnetic activity, and the configuration of the magnetosphere. Sometimes auroras appear shortly after sunset, sometimes in the early morning hours before dawn, and sometimes they're visible all night long during particularly active periods. The auroral oval itself shifts over the course of the night as Earth rotates, so the best spot to see an aurora can change from hour to hour. This is why patience is an important part of aurora watching. Sometimes the sky is quiet for hours, and then slowly, almost imperceptibly, a faint glow begins to appear on the horizon, and over the next minutes or hours it grows and develops into a full display. Other times the sky remains dark all night. Aurora watching requires a willingness to wait, to watch, and to accept that nature operates on its own schedule. There are some calm curiosities about auroras that are worth mentioning. One is the question of sound. Auroras are usually silent to most observers. They're happening so high up in the atmosphere, in such thin air, that there's no mechanism for sound to be generated in the way we normally think of it. However, some people, particularly indigenous peoples in the Arctic, and a small number of scientists and aurora watchers, have reported hearing faint sounds during auroras. These sounds are described as crackling, swishing or rustling noises, and they're very uncommon. The exact cause is still debated. One theory is that the sounds are related to electromagnetic effects during very strong auroras, perhaps causing discharges or vibrations in objects near the observer, but this remains uncertain. For the vast majority of people, auroras are a purely visual experience, silent and serene. Cameras often capture aurora colours more strongly than the naked eye. This is because camera sensors, especially those with long exposure capabilities, can accumulate light over several seconds, making faint glows much brighter and bringing out colours that your eyes might perceive as white or pale green. Your eyes are not as sensitive to colour in low light conditions. In dim environments, your vision relies more on rod cells, which are good at detecting light but not colour, while cone cells, which detect colour, are less effective. This is why a faint aurora might look greyish or pale greenish to your eyes, but appear vividly green or even red in a photograph. Long exposure photos can reveal detail and structure that you might miss with the naked eye, showing fine rays, colour gradations, and subtle movements frozen in time. This doesn't mean the camera is lying. It's just capturing light in a different way than your eyes do, integrating more photons over time and revealing what's really there. Auroras are not reflections of city lights on clouds, though this is a common misconception. They're also not caused by cold air itself, even though they're often seen in cold climates. The cold is incidental. It's just that high latitudes, where auroras are common, also happen to be cold, especially in winter. The aurora is caused by particles from space interacting with the atmosphere, not by temperature. Auroras are also not the same as meteor showers, which are caused by small pieces of rock and dust burning up as they enter the atmosphere. Meteors are brief streaks of light that last only a second or two, while auroras are glows that can persist for hours and have distinct shapes and structures. Auroras can appear above clouds, which is why mountains and high elevations can sometimes help with viewing. If you're standing on a mountaintop and there are low clouds in the valleys below, you might still see an aurora in the sky above you because the aurora is happening far higher than the clouds. Clouds are typically below 10 or 15 kilometers, while auroras start at 80 kilometers or higher, so there's no overlap. However, if there are clouds directly overhead, they'll block your view just as they would from lower elevations. Auroras can look different from minute to minute, and two people watching the same aurora can notice different colours or details based on their eyesight, the sensitivity of their eyes, and, if they're taking photos, their camera settings. Some people are more sensitive to green light, others to red. Some cameras are more sensitive to certain wavelengths. This means that your experience of an aurora is somewhat subjective, shaped by your own eyes and perception, and that's part of what makes it personal and special. Auroras are not unique to Earth. They happen on other planets in our solar system, as well wherever there's a magnetic field and an atmosphere, or at least some source of particles. Jupiter, for instance, has powerful auroras that are even more dramatic than Earth's. Jupiter's auroras are driven both by the solar wind and by material from its volcanic moon Io, which constantly spews charged particles into space. Those particles get caught in Jupiter's enormous magnetic field, which is much stronger than Earth's, and they're funneled down to the planet's poles, creating auroras that are visible in ultraviolet and infrared wavelengths. Observations from spacecraft like the Hubble Space Telescope and the Juno mission have shown that Jupiter's auroras are constantly active and incredibly bright. Saturn also has auroras, often seen in ultraviolet light by spacecraft instruments. Saturn's auroras are similar to Earth's in some ways, driven by the solar wind interacting with Saturn's magnetic field, but they also have unique features related to Saturn's magnetosphere and its interactions with its rings and moons. Even Mars, which has a much weaker global magnetic field than Earth, can show aurora-like glows. Mars lost most of its global magnetic field billions of years ago, but it still has patches of magnetized crust in certain regions, and when solar wind particles interact with those regions, they can create localized auroral glows. Mars's auroras are different from Earth's because they're not confined to polar regions. They can appear wherever there's a strong enough local magnetic field. Studying auroras on other planets teaches scientists about how atmospheres and magnetic fields interact in different environments. It's a way of testing our understanding of the physics that creates auroras, and seeing how those principles apply in places with different magnetic field strengths, atmospheric compositions, and solar wind conditions. Auroras are linked to the same physics behind many plasma phenomena in space, from solar flares to the interactions of stellar winds with exoplanets orbiting distant stars. Understanding auroras on Earth and other planets helps us understand the broader behavior of magnetized plasmas throughout the universe. The connection between the Sun and Earth is ongoing, even when we can't see it. The solar wind is always blowing, Earth's magnetosphere is always responding, and particles are always being guided toward the poles. The fact that we can't see auroras during the day or from lower latitudes doesn't mean they're not happening. The auroral oval can be tracked and forecasted using space weather data. Satellites monitor the Sun, watching for CMEs and solar flares, and they also monitor the solar wind as it flows past Earth, measuring its speed, density, and magnetic field orientation. This data allows scientists to predict when conditions are favourable for auroras and to issue forecasts and alerts for aurora watchers. These forecasts aren't perfect. Space weather is complex and difficult to predict with high precision, but they're useful for giving people an idea of when to look up. Aurora activity rises and falls with the Sun's roughly 11-year solar cycle. During solar maximum, when the Sun is at its most active, there are more opportunities for strong auroras, and the auroral oval expands more frequently, bringing auroras to lower latitudes. During solar minimum, when the Sun is quieter, auroras are less frequent and generally confined to higher latitudes. This doesn't mean there are no auroras during solar minimum. There are still quiet, steady streams of solar wind, and there can still be occasional CMEs or high-speed streams from coronal holes, any of which can produce auroras. But on average, you'll see more auroras and more intense ones during the active years of the solar cycle. Over long-time scales, auroras are part of Earth's continuing relationship with its star. They've been happening for as long as Earth has had a magnetic field and an atmosphere, which is billions of years. Ancient people saw them and created myths and legends to explain them. Some cultures thought they were spirits, others saw them as omens or messages from the gods. In some indigenous Arctic cultures, auroras were believed to be the souls of ancestors dancing in the sky. In Norse mythology, they were thought to be reflections from the shields of the Valkyries. These stories reflect the human need to understand and find meaning in natural phenomena, and they remind us that auroras have inspired awe and wonder for as long as humans have looked up at the night sky. Today, we understand the science behind auroras, and that understanding doesn't diminish their beauty. If anything, it enhances it. Knowing that you're watching energetic particles from the Sun colliding with oxygen and nitrogen atoms 100 kilometers above your head, guided there by invisible magnetic field lines, makes the experience even more remarkable. You're seeing a direct connection between Earth and the Sun, a visible manifestation of the solar wind and the magnetosphere. a process that's been unfolding for eons and will continue long into the future. Even in a quiet room, far from any aurora, Earth is moving through the solar wind. Right now, as you read this or listen to this, the solar wind is streaming past Earth. Particles are interacting with the magnetosphere, and somewhere on the planet, if conditions are right, the upper atmosphere may be softly glowing. You don't have to see it to know it's happening. Earth's magnetic field is quietly steering charged particles away from you, protecting the surface, and occasionally those particles create the gentle light shows we call auroras. It's a process that requires nothing from you, no action, no intervention. It simply happens, a natural consequence of living on a magnetized planet orbiting an active star. Auroras remind us that space is not some distant, unreachable frontier. It's right here, brushing against the edges of our atmosphere, interacting with our planet in ways both visible and invisible. The same oxygen you breathe, the oxygen that makes up about 21% of the air, can glow high above as green light when struck by particles from the sun. The same nitrogen that makes up 78% of the air can contribute blue and purple shades to an aurora. These are the same gases, just behaving differently because they are in a different environment, high and thin and energized. The dancing motion of an aurora, the way it ripples and waves and brightens and fades, is energy becoming light, and then fading back into calm. The particles collide, the atoms get excited, the energy is released as photons, and then everything settles back down, only to be excited again moments later. It's a cycle, a flow, a continuous transformation of energy from one form to another. There's something deeply soothing about that, about watching a process that's entirely natural and beyond your control, something that happens whether you're there to see it or not. Nothing about an aurora needs you to do anything. Its beauty is effortless. It doesn't ask for your attention or your approval. It simply is. You can watch it or not, photograph it or not, understand it or not, and it will continue to glow high above, following the laws of physics and the whims of the solar wind. This is true of so many natural phenomena, but auroras make it particularly clear because they're so visible and so dramatic when they occur, yet so independent of human activity. You can let your thoughts behave like aurora curtains. Let them rise, shimmer, shift, and drift away. Thoughts don't need to be held tightly or controlled any more than an aurora needs to be controlled. They can appear, glow for a while, change shape, and fade, and that's perfectly fine. There's a kind of gentle permission in that idea, a reminder that not everything needs to be managed or understood or fixed. Some things can just be observed, appreciated for what they are, and then allowed to move on. As you breathe slowly, in and out, you can rest knowing that somewhere, right now, the sky keeps its quiet glow. It might be over Alaska or Norway or Antarctica or somewhere else in the auroral oval. It might be bright and vivid, or it might be faint and subtle. Either way, it's there, steady and harmless and patient, a reminder of the ongoing connection between Earth and Sun, a visible sign of invisible processes, a light in the darkness that asks nothing of you and offers everything. The particles continue to stream from the Sun. The magnetosphere continues to guide them toward the poles. The atmospheric gases continue to glow when struck. And you, wherever you are, can close your eyes and know that this process is unfolding, has been unfolding for billions of years, and will continue long after you're asleep. The aurora doesn't need you to witness it to be real, and you don't need to do anything for it to happen. It's a gift of nature, a byproduct of the physics of our solar system, a gentle reminder that the universe is full of beauty that simply exists, whether we see it or not. The aurora will be there tomorrow night, and the night after that, and for countless nights to come, a constant, gentle presence in the polar skies, waiting for anyone who cares to look up. And when you do look up, when you stand beneath an aurora for the first time, there's often a moment of disbelief, a sense that what you're seeing can't quite be real. The lights move in ways that seem almost liquid, almost alive, and yet they're silent and distant and completely indifferent to your presence. This combination of movement and silence creates a strange dreamlike quality that many people find difficult to describe. It's not like watching a sunset which follows a predictable arc across the sky. It's not like watching stars which are fixed points of light. An aurora is dynamic but slow, energetic but gentle, brilliant but ephemeral. It exists in a category of its own, a phenomenon that doesn't quite fit with anything else in our everyday experience of the natural world. The science behind auroras is well understood now, worked out over decades of careful observation and theoretical development, but that understanding came gradually. For most of human history, auroras were mysterious. Ancient observers could see that something was happening in the sky, but they had no way to know what or why. The lights appeared without warning, moved in unpredictable ways, and disappeared just as mysteriously. Different cultures developed different explanations based on their own worldviews and mythologies. In medieval Europe, auroras were sometimes interpreted as signs of war or disaster, blood in the sky foretelling conflict. In China, they were occasionally recorded in historical texts as unusual atmospheric phenomena, though they were rare at those latitudes. In the Arctic, indigenous peoples lived with auroras as a regular part of their environment and developed rich traditions around them, some seeing them as playful spirits, others as dangerous forces to be respected. It wasn't until the scientific revolution that people began to approach auroras with the tools of systematic observation and experimentation. In the 18th century, scientists started to notice patterns. Auroras seemed to be more common at certain latitudes. They seemed to vary in frequency over time, becoming more common during some years and less common during others. Careful observers noted that auroras often appeared to align roughly north-south, following what we now know are magnetic field lines. But the mechanism remained a mystery. How could light appear in the sky without any apparent source? What was making the air glow? The breakthrough came in stages. In the 19th century, scientists discovered that Earth has a magnetic field, and they began to map its shape and strength. They also discovered that the sun was not a static object but showed features like sunspots that varied over time. Some observers noticed a correlation between sunspot activity and the frequency of auroras, suggesting a connection between the sun and these atmospheric lights. But the nature of that connection remained unclear. What was travelling from the sun to Earth? How was it causing the atmosphere to glow? The answer required understanding that the sun emits more than just light. In the early 20th century, scientists proposed that the sun releases streams of charged particles, and in the 1950s and 1960s, this solar wind was finally detected and measured by spacecraft. Around the same time, scientists worked out the details of how charged particles interact with magnetic fields and how they can be guided along field lines. They developed the theory of the magnetosphere, understanding that Earth's magnetic field creates a protective bubble that shapes the flow of the solar wind around the planet. They figured out that particles can be trapped in the magnetosphere, bouncing back and forth along field lines, and that under certain conditions they can be accelerated downward into the atmosphere where they collide with gases and produce light. This understanding brought together physics from many different domains: electromagnetism, plasma physics, atomic physics, atmospheric science. Auroras turned out to be a window into processes happening throughout the solar system and beyond. They became a subject of serious scientific study, with dedicated research programs, satellite missions, and ground-based observatories all working to understand the details. Today, we have a comprehensive picture of how auroras work, though there are still details being refined and new discoveries being made. Science is never truly finished. It's always finding new layers of complexity and new questions to ask. One of the interesting things about auroras is that they're both local and global. They're local in the sense that they happen in specific places, the auroral ovals around the poles, and if you're not in those places, you won't see them. But they're global in the sense that they're the result of processes that affect the entire magnetosphere, the entire relationship between Earth and the Sun. When a coronal mass ejection leaves the Sun, it affects the entire dayside magnetosphere when it arrives. The compression and energy input ripple through the system, affecting the magnetotail, the particle populations trapped in various regions, and the coupling between the magnetosphere and the ionosphere. The aurora you see in Alaska is connected to processes happening on the other side of the planet, in the magnetotail stretching millions of kilometers into space, and to events that occurred on the Sun days earlier. It's all one interconnected system. The ionosphere is another important player in the aurora story. The ionosphere is the part of the upper atmosphere, where there are enough free electrons and ions to affect the propagation of radio waves. It overlaps with the region where auroras occur, roughly from about 60 to 1,000 kilometers altitude. During an aurora, the incoming particles increase the ionization in the ionosphere, creating more free electrons and ions. This can affect radio communications and GPS signals, sometimes causing disruptions or errors. This is one reason why understanding and forecasting auroras is not just a matter of scientific curiosity, it has practical applications. Airlines flying polar routes need to know about space weather conditions because increased radiation during geomagnetic storms can pose risks to passengers and crew at high altitudes. Satellite operators need to know because increased drag from the swollen upper atmosphere during storms can affect satellite orbits. Power grid operators need to know because geomagnetic storms can induce currents in long power lines, potentially damaging transformers. The connection between auroras and technology is a reminder that we live in a technological civilization that depends on infrastructure extending into space and operating in the upper atmosphere. That infrastructure is affected by space weather, and auroras are one visible sign of space weather in action. The same geomagnetic storm that creates beautiful auroras can also create problems for GPS, communications, and power grids. It's a dual nature, beautiful and potentially disruptive, a natural phenomenon that we admire and also have to manage. But most of the time, auroras are simply beautiful and harmless. For every geomagnetic storm that causes technological issues, there are dozens or hundreds of quiet auroral displays that do nothing but light up the polar skies. These quieter auroras are the result of the steady background solar wind interacting with the magnetosphere in a more gentle way. They're less dramatic than the big displays during storms, but they're more common, and they're just as real, just as much a part of the ongoing Sun-Earth connection. Watching an aurora can be a meditative experience. There's a stillness required, a willingness to stand outside in the cold, often for hours, just watching the sky. Many aurora watchers describe a sense of peace that comes from this. You're not in control of whether the aurora appears or how bright it is or how long it lasts. You're simply there, a witness, watching something unfold according to its own logic. This kind of patient observation is increasingly rare in modern life, where so much is instant and controllable. An aurora can't be summoned or paused or replayed. It happens in real time, and if you miss it, it's gone. This ephemerality is part of its charm. Photographers have a different relationship with auroras. For them, the aurora is both a subject and a challenge. Capturing an aurora well requires technical skill, knowing how to set a camera for long exposures, how to focus in the dark, how to balance the brightness of the aurora with the darkness of the sky, how to include interesting foreground elements without letting them become silhouettes. Many aurora photographers spend years refining their technique, learning the best settings for different conditions, scouting locations during the day so they know where to set up at night. The results can be stunning, images that reveal details and colours that are barely visible to the naked eye. But even the best photograph is just a representation, a frozen moment extracted from a dynamic flowing display. The real aurora is always richer, always more complex than any single image can capture. There's also a social aspect to aurora watching. In places where auroras are common, communities develop around them. People share forecasts and sightings, they gather in favourite viewing spots, they exchange tips about where to go and when. Online communities have formed where aurora watchers from around the world post photos, discuss conditions and share their excitement. For some people, chasing auroras becomes a passion, even an obsession. They travel to remote locations, they plan trips around solar activity forecasts, they stay up all night in freezing temperatures just for the chance to see a particularly good display. This dedication might seem extreme to outsiders, but for those involved, it's entirely logical. Auroras are worth the effort, worth the discomfort, worth the time and expense because they offer something that few other experiences can match: a direct, visible connection to the cosmos, a reminder of our place in a vast and dynamic universe. For scientists, auroras are not just beautiful, they're data. Every aurora is a measurement, a record of conditions in the magnetosphere and the solar wind. Ground-based instruments measure the aurora's brightness and colour. Radar systems track the motions of particles in the ionosphere. Magnetometers measure disturbances in Earth's magnetic field. And all of this data goes into building a more complete picture of how the Sun-Earth system works. Satellites in orbit above the atmosphere can look down on auroras from above, seeing their full extent and structure in ways that are impossible from the ground. These overhead views reveal that the auroral oval is not a perfect ring, but an irregular band that shifts and pulses, with bright patches and dark regions, with streamers and arcs that extend and contract over the course of minutes. Some satellites carry instruments that can measure the particles themselves, flying through the regions where auroras are being generated and directly sampling the electrons and ions responsible for the light. These measurements have shown that auroral particles can have a wide range of energies, from a few electron volts to tens of thousands of electron volts. The higher energy particles penetrate deeper into the atmosphere, creating lower altitude auroras with different colours. The lower energy particles are stopped higher up. By combining measurements from many different instruments, ground-based, airborne and space-based, scientists can build up a three-dimensional picture of an aurora, understanding not just what it looks like, but how it's produced, what particles are involved, where they came from, and how they were accelerated. One particularly interesting finding from this research is that auroras are not evenly distributed in time. They tend to occur in bursts with periods of enhanced activity followed by quieter periods. These bursts are related to substorms, which are episodes of energy release in the magnetotail. During a substorm, the aurora suddenly brightens and becomes more active, often spreading toward the equator and developing rapid motions and complex structures. The substorm then gradually subsides over the course of an hour or so, and the aurora returns to a quieter state. Substorms can occur several times during a single night, creating a rhythm of activity and calm. The triggers for substorms are still being studied, and while the basic outline is understood, energy builds up in the magnetotail and is released through magnetic reconnection. The details of when and why a substorm begins are complex and not fully predictable. The magnetotail itself is a fascinating structure. It's created by the solar wind dragging Earth's magnetic field lines downwind, stretching them out into space like a windsock. The magnetotail has two lobes, a northern lobe and a southern lobe, separated by a current sheet where the magnetic field reverses direction. This is a region of particular interest because it's where reconnection often occurs. When reconnection happens in the magnetotail, it releases energy that drives particles earthward, and some of those particles end up creating auroras. But reconnection is a complex process, involving the rearrangement of magnetic field lines on very small scales so small that they require specialized instruments and sophisticated simulations to study. Understanding reconnection is not just important for understanding auroras, it's important for understanding magnetic phenomena throughout the universe, from solar flares to the dynamics of distant astrophysical plasmas. Auroras also have a seasonal variation that's not immediately obvious. You might think that auroras would be equally common throughout the year, but observations show that they're actually more frequent around the equinoxes, the spring and fall, than around the solstices, the summer and winter. This is called the Russell-McFerran effect, and it has to do with the orientation of Earth's magnetic field relative to the magnetic field carried by the solar wind. During the equinoxes, the geometry is more favourable for the solar wind magnetic field to couple efficiently with Earth's magnetic field, allowing more energy to be transferred into the magnetosphere. During the solstices, the geometry is less favourable, and while auroras still occur, they're somewhat less frequent. This effect is subtle, and there are many other factors that influence aurora activity, but over long periods and large datasets, the equinoctial enhancement is clearly visible. The Earth's magnetic field is not static. It changes over time. On short timescales, it responds to the solar wind, being compressed and stretched and disturbed by geomagnetic storms. On longer timescales, it has its own internal dynamics. The magnetic poles wander slowly over decades and centuries, and occasionally over thousands or millions of years, the magnetic field reverses entirely, with north and south swapping places. During a reversal, the field weakens and becomes more complex, and it's thought that auroras might appear at unusual latitudes or have different characteristics. However, no human has ever observed a magnetic field reversal. The last one happened about 780,000 years ago, long before modern humans existed. What would auroras look like during a reversal? We can only speculate using computer models and theoretical understanding, but it's an intriguing question. The fact that other planets have auroras tells us that the basic physics of auroras is universal. Wherever you have a magnetic field, an atmosphere or at least some source of neutral particles, and a source of energetic charged particles, you can have auroras. On Jupiter, the auroras are driven partly by the solar wind and partly by volcanic material from Io that gets ionized and caught in Jupiter's magnetic field. On Saturn, interactions with the rings and moons add complexity to the auroral processes. On Uranus and Neptune, the magnetic fields are tilted at extreme angles relative to the planet's rotation axis, creating auroral patterns that are quite different from Earth's. Studying these alien auroras helps us understand the diversity of magnetospheric systems and tests our theories in environments very different from Earth. Even some moons have auroras. Ganymede, one of Jupiter's large moons, has its own small magnetic field, and it experiences auroras when particles from Jupiter's magnetosphere interact with that field. This makes Ganymede the only moon in the solar system known to have its own auroras, a unique status that highlights the importance of magnetic fields in creating these light displays. Without a magnetic field, a moon or planet can still have airglow, a faint luminescence from chemical reactions in the atmosphere, but it won't have the structured, dynamic auroras that we see on magnetized bodies. Back on Earth, the study of auroras has also led to advances in related fields. Understanding how particles are accelerated in the magnetosphere has applications to understanding particle acceleration elsewhere in the universe, such as in supernova remnants or around black holes. Understanding magnetic reconnection in Earth's magnetotail has informed studies of reconnection in solar flares and in laboratory fusion experiments. The techniques developed for remote sensing of auroras, using optical instruments, radar and satellites, have been adapted for studying other atmospheric and space phenomena. In science, understanding one thing often leads to understanding many things, as the same physical principles apply in different contexts. There's also a human dimension to aurora science. The scientists who study auroras are people with their own motivations and passions. Many of them were inspired to enter the field because they saw an aurora and wanted to understand it. They've spent years, sometimes decades, building instruments, analysing data, writing papers, and piecing together the puzzle of how auroras work. They've stood on frozen tundra deploying equipment. They've flown on research aircraft through auroral arcs. They've launched sounding rockets to sample the upper atmosphere. They've written computer codes to simulate magnetospheric dynamics. Their work is a testament to human curiosity, to the drive to understand the natural world not for immediate practical gain, but simply because it's there, because it's fascinating, because knowing is better than not knowing. For the rest of us who may not be scientists, auroras offer something different but equally valuable. They offer beauty, wonder, and a sense of connection. When you stand beneath an aurora, you're standing beneath a phenomenon that links you to the sun, to the Earth's interior where the magnetic field is generated, to the thin upper atmosphere, to the solar system and the cosmos beyond. You're part of a planet in motion through space, constantly bathed in the solar wind, protected by a magnetic shield, home to an atmosphere that can light up when energized. This perspective, this sense of context and connection, is something that's easy to lose in daily life. Auroras restore it, at least for a moment, and there's a timelessness to auroras. The aurora you see tonight is the same phenomenon that people saw 1,000 years ago, 10,000 years ago, 1,000,000 years ago. The details change, the solar wind fluctuates, the magnetic field drifts, the atmosphere evolves slowly over geological time, but the basic process is the same. Auroras are ancient, recurring, part of the fabric of Earth's existence. They'll still be happening long after we're gone, long after human civilization is a distant memory, as long as the sun continues to shine and Earth retains its magnetic field and atmosphere. There's something comforting in that continuity, a reminder that we're part of something much larger and longer lasting than our individual lives. When you think about auroras in this way, as part of deep time and cosmic processes, they become more than just pretty lights. They become a link to the past and the future, a manifestation of forces that have shaped our planet and will continue to shape it. The same solar wind that creates auroras also plays a role in the long-term evolution of planetary atmospheres. On Mars, which lost its global magnetic field early in its history, the solar wind has been slowly stripping away the atmosphere over billions of years. On Earth, our magnetic field protects us from this fate, deflecting the solar wind and preserving our atmosphere. Auroras are a side effect of that protection, a visible reminder that we live on a shielded world. The colours of an aurora, too, carry information about the state of the atmosphere. The green line from oxygen, at 557.7 nanometers, is one of the most studied features in atmospheric physics. It's called a forbidden transition because it's very unlikely to occur under normal conditions. The oxygen atom has to remain undisturbed for almost a full second before it can emit this particular wavelength. In denser parts of the atmosphere, the atom would collide with another particle long before it had a chance to emit the green light. But at auroral altitudes, the air is so thin that collisions are rare enough for the forbidden transition to happen. This is why the green line is so prominent in auroras but rarely seen at lower altitudes. It's a signature of the thin, rarefied air of the thermosphere. The red line from oxygen, at 630 nanometers, requires even longer for the atom to emit, about 2 minutes of remaining undisturbed. This means it only shows up at even higher altitudes, above about 200 kilometers, where the air is extremely thin. When you see red in an aurora, you're seeing light from a very high, very rarefied part of the atmosphere, a region that's more space than air. The fact that we can see this light at all from the ground, from hundreds of kilometers away, is remarkable. The atmosphere at those altitudes is so tenuous that a handful of air would contain only a few million molecules compared to trillions per handful at sea level. And yet, when energized, even that thin scattering of atoms can glow brightly enough to be visible to the naked eye. Nitrogen contributes its own set of spectral lines, creating blues and purples, especially at lower altitudes. Nitrogen molecules can be excited in different ways, leading to different emission lines, and the mix of these lines determines the exact shade you see. Sometimes nitrogen creates a deep purple red at the lower edges of auroral curtains, sometimes a blue or violet tinge. The exact colour depends on the energy of the incoming particles and the density of the atmosphere at that altitude. It's a complex chemistry, with dozens of possible reactions and transitions, all happening simultaneously, all contributing to the overall glow. There's also a phenomenon called auroral kilometric radiation, which is radio emission generated by auroras. It's not visible to the eye and can't be heard with the ear, but it can be detected by radio receivers. This radiation is produced by the same population of electrons that creates the visible aurora, but through a different mechanism involving the interaction of the electrons with the magnetic field. Auroral kilometric radiation can be quite strong and can actually be detected from space, allowing satellites far from Earth to monitor auroral activity. It's one more piece of the puzzle, one more way that auroras manifest, extending beyond the visible spectrum into radio waves. In recent years, citizen scientists have contributed to aurora research in meaningful ways. Amateur photographers capture auroras from locations around the world, providing data on timing, location, and appearance that complement scientific observations. Some projects invite people to submit their aurora photos along with metadata about when and where they were taken, and this crowdsourced data helps scientists track the movement and evolution of auroral displays over large geographic areas. Other projects use networks of cameras operated by volunteers to monitor the sky continuously, creating time-lapse records of auroral activity. This collaboration between professional scientists and interested amateurs is a reminder that science is not just for experts in laboratories. It's for anyone with curiosity and a willingness to observe carefully. There are also aurora apps and websites that provide forecasts and alerts. These services use real-time data from satellites and ground stations to predict when and where auroras are likely to be visible. They can send notifications to your phone when conditions look promising, helping you decide whether it's worth venturing out to try to see an aurora. The forecasts are based on measurements of the solar wind taken by spacecraft positioned upstream of Earth, at a point called L1 where the gravitational pull of the Sun and Earth balance out. These spacecraft can see the solar wind about an hour before it reaches Earth, giving forecasters a short but useful warning time. If the solar wind is carrying a southward-pointing magnetic field, conditions are favourable for auroras because that orientation couples well with Earth's northward-pointing field, allowing energy transfer. If the magnetic field is pointing northward, coupling is less efficient and auroras are less likely. The forecasting of auroras has improved significantly over the years, but it's still not perfect. Space weather is inherently unpredictable in some ways because it depends on processes happening on the Sun and in the magnetosphere that we can't control or predict with complete accuracy. A CME might arrive earlier or later than expected. Its magnetic field orientation might change as it travels through space. Reconnection in the magnetotail might start suddenly, or might fail to start at all. These uncertainties mean that aurora forecasts are probabilistic rather than deterministic. They can tell you that conditions are likely to be favourable, but they can't guarantee that you'll see an aurora. This is part of the adventure, part of the reason aurora watching requires patience and a bit of luck. Some of the most memorable auroras are the ones that appear unexpectedly when you weren't planning to watch for them. You step outside for an unrelated reason, and there it is. A glow in the sky, a curtain forming overhead. These surprise auroras have a special quality because they're not anticipated, not planned for. They're a gift, a reminder that the natural world operates on its own schedule and sometimes offers beauty when you're not even looking for it. Many people have stories like this, of seeing their first aurora by accident, of being in the right place at the right time without even knowing that auroras were possible. The experience of seeing an aurora can vary tremendously, depending on where you are and what the conditions are like. An aurora seen from the middle of a city, fighting against light pollution, might be just a faint glow, barely distinguishable from the general sky brightness. The same aurora seen from a dark location in the countryside can be vivid and detailed, with clear colours and structure. An aurora at the edge of the auroral oval, just barely visible on the horizon, is a different experience from an aurora directly overhead, filling the sky from horizon to horizon. A quiet, steady arc is different from a fast-moving, pulsating display. All of these are auroras, all valid, all beautiful in their own way, but they offer different experiences. There's also a difference between watching an aurora alone and watching one with others. Watching alone can be meditative and personal, a one-on-one encounter with nature. Watching with friends or family can be social and shared, with exclamations and pointing, and the joy of experiencing something remarkable together. Watching with a group of strangers, perhaps at a popular viewing location, can create a sense of community, a feeling that you're all witnesses to the same event, all connected by the shared experience. There's no right way to watch an aurora. It depends on your temperament and the circumstances. For some people, the appeal of auroras is primarily aesthetic. They're drawn to the beauty, the colours, the motion, the visual spectacle. For others, the appeal is more intellectual, rooted in an appreciation for the science and a desire to understand the mechanisms. For still others, the appeal is emotional or even spiritual, a sense of awe and wonder that connects them to something larger than themselves. All of these responses are valid, and they're not mutually exclusive. You can appreciate the beauty and the science and the sense of wonder all at the same time. In fact, understanding the science often enhances the sense of wonder rather than diminishing it. Knowing that the green light comes from oxygen atoms relaxing from an excited state doesn't make the green any less beautiful. It makes it more meaningful. As the night deepens and the aurora continues its dance, there's a rhythm to watching that settles in. Your eyes adjust to the darkness, your body adjusts to the cold, and your mind enters a state of quiet attention. You're not thinking about your daily concerns or your plans for tomorrow. You're simply present, watching the sky, noticing the changes, the brightening and dimming, the shifts in colour and form. This kind of present moment awareness is rare and valuable. It's a form of meditation, though you might not think of it that way. You're anchored in the here and now by the aurora itself, which demands nothing from you except attention. Time can seem to stretch during an aurora display. Minutes feel longer, hours pass without notice. You might think you've been outside for 20 minutes when it's actually been an hour, or you might feel like you've been watching for ages when it's only been a few minutes. This distortion of time perception is common during absorbing experiences, and it's another sign that watching an aurora pulls you out of your normal mental state and into something different, something more focused and immediate. Eventually the aurora fades, the particles slow, the energy decreases, the glow diminishes, the curtains soften and dissolve, the arcs fade into the background sky, and the stars, which had been outshone by the aurora, become visible again. The sky returns to its normal darkness and the show is over. This ending is bittersweet. You're grateful to have seen it, but you also feel a sense of loss as it disappears. Many aurora watchers will stay outside even after the aurora has faded, hoping it might return, and sometimes it does. A new surge of particles arrives, a new substorm begins, and the aurora flares up again, giving you a second show. Other times, the sky remains dark, and you know the display is truly over for the night. Walking back inside after watching an aurora, you often feel changed in some small way. It's hard to articulate exactly how, but there's a sense of having witnessed something important, something worth the cold and the late hour and the effort. You carry the memory of it with you, and for days or weeks afterward, you might find yourself thinking about it, replaying the images in your mind, feeling again the quiet awe you felt while watching. These memories can be a source of comfort and inspiration, a reminder that the world holds beauty and wonder if you take the time to look for it. The next story is about to begin. Please relax and enjoy. Welcome to a quiet place. A place where the only task ahead of you is to let your mind wander gently through the soft glow of starlight and to let each thought settle like dust on a calm surface. Tonight, we're going to explore the Milky Way, not as something distant and unreachable, but as the quiet, familiar home it truly is. You're already inside it. Right now, as you rest, you're tucked into one small corner of this vast, slowly turning collection of stars and dust and silent space. There's nothing to do but listen and breathe and let these small facts drift past you like clouds across a dark sky. We'll move through exactly 100 gentle observations about the Milky Way. Small pieces of understanding, each one simple enough to hold for a moment before releasing it. There's no hurry, there's no test. There's only the soft rhythm of learning, like counting stars until the counting itself becomes a kind of rest. So settle in, let your breathing slow. Picture, if you can, a pale river of light stretched across a perfectly dark sky, a band of softness against the black. That image, that quiet glow, is where we'll spend our time tonight. The Milky Way is the galaxy that contains our solar system. This is the first fact, and perhaps the most grounding. When you look up on a clear, dark night and see that hazy band stretching overhead, you're not looking at something separate from yourself. You're looking at the structure you're already part of. The Milky Way isn't a distant object in the sky. It's the neighborhood. It's home. Our sun, our Earth, the moon, all the planets, every comet and asteroid and speck of dust in our solar system. They all belong to this one galaxy. The Milky Way is the cosmic address that holds everything familiar to us. A galaxy is a vast collection of stars, gas, dust, and dark matter held together by gravity. To understand the Milky Way, it helps to understand what a galaxy is in the first place. Imagine gathering hundreds of billions of stars, more stars than you could count in many lifetimes, and letting gravity pull them into a single organized structure. But it's not just stars. Between the stars, there's gas, mostly hydrogen, drifting in enormous clouds. There's dust, made of tiny solid particles scattered throughout, and woven through everything, invisible but essential, is dark matter, a kind of mass that doesn't emit light, but whose gravity helps hold the whole structure together. All of this, bound by the patient, inexorable pull of gravity, forms what we call a galaxy. From Earth, we see the Milky Way as a hazy band because we're viewing it from inside. This is one of those facts that feels almost strange once you think about it. If you were outside the Milky Way, looking back from a great distance, you might see it as a beautiful spiral, arms of stars curving outward from a bright centre. But we don't have that view. We're embedded in the structure itself, sitting somewhere in the disk, looking along the plane. So when we look toward the densest parts of the galaxy, what we see is a band, a soft milky stripe, because we're seeing the combined light of countless stars stretching away in both directions. It's like standing in the middle of a forest and looking horizontally through the trees. You see depth, layers, a sense of many trunks receding into shadow. That's the view we have of our own galaxy. That hazy glow is the combined light of many distant stars. Each point of light you can resolve individually as a single star, probably relatively nearby in cosmic terms. But the soft glow, the diffuse brightness that makes the band look like spilled milk, that comes from stars too far away or too faint to see as separate points. Your eye blends them together into a continuous shimmer. It's a visual echo of distance, of sheer number. There are so many stars along those sightlines that their light merges, creating that gentle, pervasive glow. The band looks brightest, where the star density is highest. This makes sense once you think about it, but it's worth savouring. The Milky Way isn't uniformly bright. Some parts of the band are richer, more luminous. Those are the directions where stars are more tightly packed, where the disk is thicker, or where we're looking through more layers of the galaxy's structure. Other parts are dimmer, either because there are fewer stars in that direction, or because dust is blocking the light. The variation is subtle, but if you've ever watched the Milky Way on a truly dark night, you've seen how it swells and fades, how certain regions seem to glow more intensely, while others are almost ghostly. Milky Way, is a name inspired by its soft spilled light appearance. The name itself is ancient, though the exact origins vary by culture. In English, Milky Way evokes the image of milk poured across a dark surface, an apt metaphor for that pale, clouded band. Other cultures have called it a river, a path, a bridge. The common thread is softness, a sense of something flowing or spilled or gently laid across the heavens. It's a name that invites calm. There's nothing harsh about it. It's not the blazing belt or the fierce stripe. It's milky, quiet, almost comforting. The galaxy has a flattened disk shape rather than a perfect sphere. If you could step outside and view the Milky Way edge-on, you'd see that it's quite thin relative to its width. Imagine a dinner plate, or better yet, two dinner plates placed rim to rim with a slight bulge in the middle. That's closer to the Milky Way's shape than a ball or a cloud. Most of the stars, especially the younger ones, are organised into this flat disk. The disk rotates slowly, and that rotation helps maintain its flatness. It's a consequence of angular momentum and gravity working together over billions of years. The disk contains many of the stars we can see in the night sky. When you look up and pick out individual stars, Sirius, Vega, Betelgeuse, most of those are part of the Milky Way's disk. They're our neighbours in this vast structure. Some are closer, some farther, but they share the same general plane, the same galactic environment. The disk is where much of the galaxy's visible activity happens, where new stars are born, where spiral arms wind slowly outward. The Milky Way also has a central bulge of stars. At the very heart of the galaxy, the disk thickens into a bulge, a more densely packed region of stars. These stars are often older, redder, having burned for billions of years. The bulge is brighter than the outer disk, though from Earth, dust often obscures our view of it. If you could see through all that dust, the central bulge would dominate the view, a warm glow at the galaxy's core. Surrounding everything is a large, faint halo. The halo is less obvious, harder to see, but it's there. A vast, roughly spherical region that extends far beyond the disk. The halo contains old stars, ancient star, clusters, and is thought to hold much of the galaxy's dark matter. It's like a diffuse envelope around the more structured disk and bulge, a reminder that the Milky Way's influence extends far beyond its bright, visible parts. Just one more small fact, and then we drift. Our solar system sits inside the Milky Way's disk. This is your location, cosmically speaking. You're not in the halo, not in the central bulge, but in the disk, somewhere in the suburbs of the galaxy, you might say. The disk is where the action is, where gas and dust provide the raw materials for new stars, where spiral arms trace slow patterns. You're embedded in that environment, part of that ongoing story. We're not near the very centre of the galaxy. In fact, we're quite far out. The galactic centre lies roughly 26,000 light-years away, a distance so vast that light from the centre, travelling at its tremendous speed, takes 26,000 years to reach us. We're out in a quieter region, away from the crowded, energetic core. This is probably fortunate. The centre is a busy, intense place, full of tightly packed stars and powerful forces. Out here, there's more room, more calm. We orbit the galactic centre like a slow, wide carousel. Just as Earth orbits the Sun, and with it, our entire solar system, orbits the centre of the Milky Way. It's a grand, sweeping orbit, far larger and slower than anything we experience in our daily lives. We're moving through space at a speed of roughly 200 kilometers per second relative to the galactic centre, but the orbit is so large that it takes an immense amount of time to complete even one circuit. This orbit takes a very long time compared with a human life. Estimates suggest it takes about 200 to 250 million years for the Sun to make one full orbit around the galaxy. This span of time is called a galactic year, or sometimes a cosmic year. To put that in perspective, the last time the Sun was in this exact spot in its orbit, dinosaurs had not yet appeared on Earth. The whole history of human civilization is a tiny fraction of one galactic orbit. The Milky Way's rotation is a deep, slow rhythm, far removed from the pace of human experience. Even while you lie still, Earth is moving through space. Right now, as you rest, you're travelling. Earth is spinning on its axis, orbiting the Sun, and the Sun is carrying you along on its orbit around the galaxy, and the galaxy itself is moving relative to other galaxies. There are layers of motion, each one imperceptible in the moment but real and ongoing. It's a gentle thought, really. You don't have to do anything to be part of this motion. You're already moving, already journeying through space, even in stillness. That motion is shared. Planets, stars, and gas all drift together. The sun doesn't orbit alone. It carries its planets, its asteroids, its distant comets, all moving together as a single family. And nearby stars are doing the same, each one following its own orbit, all of them drifting along together like a slow-moving river. The Milky Way is not a rigid structure. It's a dynamic flow of matter, each piece responding to gravity's pull, each orbit contributing to the whole. The Milky Way is so large that here and there can be separated by vast distances. The galaxy is roughly 100,000 light-years across, a span so enormous that it defies easy comprehension. If you could send a message at the speed of light from one side of the galaxy to the other, it would take 100,000 years to arrive. Within that expanse, stars are separated by light-years, sometimes many light-years. Space is not crowded. There's room, emptiness, silence between the points of light. Most stars you see are relatively nearby in galactic terms. When you look at the night sky and see individual stars, you're mostly seeing stars that are within a few hundred or a few thousand light-years of Earth. That might sound like a lot, but in a galaxy 100,000 light-years wide, it's the immediate neighbourhood. The vast majority of the Milky Way's stars are too far away to resolve individually with the naked eye. They contribute to that diffuse glow, but they don't stand out as separate points. Many stars in the Milky Way are too faint to see with the naked eye. Even the brightest star in the galaxy would appear faint if it were far enough away. And most stars are not especially bright to begin with. Small, dim, red stars outnumber the bright, massive ones. These dim stars, red dwarfs for example, can shine steadily for trillions of years, but they're so faint that even relatively nearby ones can be invisible without a telescope. The Milky Way is full of these quiet, unassuming stars, far more numerous than the brilliant giants we notice. Night skies look different depending on dust, light pollution, and your location. If you've ever seen the Milky Way from a truly dark site, far from city lights under clear skies, you know how striking it can be. But light pollution washes out that view for much of the world. Dust in Earth's atmosphere can also scatter light and reduce contrast. And your latitude matters too. From some locations, certain parts of the Milky Way are always below the horizon. The view is variable, a reminder that what you see is shaped by where you are and what conditions allow. Just one more small fact, and then we drift. The Milky Way band is brightest in truly dark skies. This is worth emphasizing because it's becoming rarer. As artificial light spreads, fewer people have the chance to see the Milky Way in its full glory. But in places far from human lights, where the sky is a vault of pure darkness, the Milky Way can be astonishingly bright. It can cast faint shadows. It can dominate the sky, a river of light stretching from horizon to horizon. That brightness is a measure of how many stars there really are, and how much light they produce when nothing interferes with the view. The band is made of countless unresolved stars. Each time we say this, it's worth pausing on the word countless. Not uncountable in principle. Someone with enough patience and a good telescope could catalogue them, but countless in the practical sense. Too many to keep track of, too many to name, too many to ever know individually. They blend together, and in that blending they create something beautiful. A collective glow that represents the shared light of billions. Dark lanes in the band are clouds of dust blocking starlight. If you've seen detailed images of the Milky Way, you've probably noticed dark patches, gaps in the glow. These aren't empty regions. They're clouds of dust thick enough to block the light of stars behind them. The dust particles themselves are tiny, far smaller than grains of sand, but there are so many of them, spread across such vast volumes, that they can dim or completely obscure starlight. These dark lanes give the Milky Way texture, depth, a sense of structure. Dust doesn't turn off stars, it simply hides their light from our view. This is an important distinction. The stars behind those dark clouds are still there, still shining. They haven't been extinguished. It's just that their light, travelling through space, encounters dust along the way, and that dust absorbs or scatters the light before it can reach us. From another angle, from a different vantage point, those same stars might be perfectly visible. It's a matter of perspective, of what lies between the observer and the source. The galaxy's disk is filled with gas and dust along with stars. The Milky Way is not a sterile environment. Between the stars, there's material, mostly hydrogen gas, but also dust, molecules, heavier elements. This interstellar medium, as it's called, is incredibly diffuse by everyday standards, far more tenuous than the best vacuum we can create on Earth. But over the vast distances of space, even that thin, material adds up. It's the raw material for new stars, and it also shapes what we see when we look through the galaxy. Dust grains are tiny, but there are so many that they can dim light across huge regions. A single dust grain is microscopic, perhaps a fraction of a micrometer across. But space is vast, and when you look through a cloud of dust, you're looking through countless trillions of these grains. Each one scatters or absorbs a tiny bit of light. Collectively, they can reduce starlight significantly, reddening it and dimming it or blocking it entirely. It's a reminder that even the smallest things, given enough numbers and enough space, can have profound effects. When you see a rift in the Milky Way, you're often seeing dust silhouettes. The Great Rift, for example, is a prominent dark lane that runs along much of the Milky Way's length in the summer sky, as seen from the northern hemisphere. It's not a gap in the stars. It's a foreground curtain of dust blocking the light of more distant stars. The rift has structure, texture, because the dust clouds have structure. They're not uniform blankets. They're clumpy, filamentary, shaped by gravity and magnetic fields and the motions of gas. The band arches across the sky because we're inside a disk looking along its plane. This is another consequence of our location. The disk of the Milky Way is oriented in space, and from Earth, that orientation makes the band appear to curve across the sky. In some seasons the band is higher, in others lower or barely visible, but its arching path is always a reflection of the disk's geometry and our place within it. If we could step outside and view the galaxy from above or below, the disk would appear flat, but from inside it arches. Looking away from the plane, the sky can look darker and more open. If you're under a dark sky and you look toward a direction perpendicular to the Milky Way's plane, you're looking out of the disk toward intergalactic space. There are fewer stars in that direction, less foreground material. The sky appears darker, more empty, though of course it's not truly empty. There are still stars, and beyond them, distant galaxies. But the density drops, and the visual effect is one of openness, of looking out rather than through. The Milky Way is less a stripe on the sky, and more the structure you're inside. This shift in perspective is subtle but important. The Milky Way isn't painted on the sky like a decoration. It's the environment. You're not looking at it from the outside, you're looking through it, around it, within it. Every direction you look, you're seeing some part of the Milky Way, some density of stars and dust. The band is just the direction where that density is highest, where the view extends deepest into the structure. Just one more small fact, and then we drift. The Milky Way has spiral structure, like gently curved lanes. If you could view the Milky Way from above, you'd see that it's not just a featureless disk. It has arms, spiral arms, curving outward from the central regions like the arms of a pinwheel. These arms aren't solid objects. They're regions where stars and gas are more concentrated. The spiral pattern rotates, though not like a solid wheel, is more like a wave, a pattern that moves through the disk, organizing stars and gas into these graceful curves. Spiral arms are regions where gas and stars are more concentrated. Think of the arms as traffic jams in the disk. Material moves into the arms, slows down due to gravity, and piles up. This increased density makes the arms brighter, easier to see. They're also where much of the star formation happens, because the higher density helps trigger the collapse of gas clouds into new stars. The arms are dynamic, evolving, a sign that the galaxy is not static but actively shaping itself. Arms are not solid objects, but patterns within a rotating disk. This is one of those concepts that takes a moment to grasp. You might imagine the spiral arms as fixed structures, like the blades of a fan rotating together. But that's not quite right. The arms are density waves, patterns that move through the disk at a different speed than the stars themselves. A star might pass into an arm, spend some time in that denser region, and then pass out the other side. The arm persists, but the material within it changes. It's a dynamic equilibrium, a pattern that endures even as the individual pieces flow through it. The central bulge is a thicker, brighter region of stars. If the disk is a flat plane, the bulge is a swelling at the center. a concentration of stars in a more spherical or elliptical shape. The bulge is old, dense, and bright. It contains a huge number of stars packed more tightly than in the outer disk. If you were somehow able to stand near the galactic centre, ignoring all the practical impossibilities, the night sky would be astonishingly bright, filled with stars visible in every direction. The bulge contains many older stars. The stars in the bulge tend to be redder, cooler, older. They were born long ago in the early history of the galaxy, and they've been orbiting the centre ever since. These are not the hot, blue, short-lived stars you might find in active star-forming regions. They're the long-lived survivors, stars that have settled into a slow, steady burn, contributing their warm light to the bulge's glow. A halo extends beyond the main disk in all directions. The halo is harder to visualize because it's so diffuse and faint. It's not a sharp boundary. It fades gradually into the darkness of intergalactic space. But it's there, a vast region surrounding the disk and bulge, containing old stars, globular clusters, and a lot of dark matter. The halo is ancient, a relic of the galaxy's formation, and it extends far beyond the visible parts of the Milky Way. The halo contains older stars and star clusters. The stars in the halo are among the oldest in the galaxy, some approaching the age of the universe itself. They're metal poor, meaning they have fewer heavy elements than younger stars, because they formed before many generations of stellar recycling had enriched the galaxy with heavier elements. The globular clusters, tight spherical groups of stars, are particularly prominent in the halo, each one a dense community of ancient suns. The halo is also where much of the galaxy's dark matter is thought to be. Dark matter doesn't emit light, so we can't see it directly, but we can infer its presence from the way visible matter moves. The rotation curve of the Milky Way, how fast stars and gas orbit at different distances, suggests there's much more mass than we can see. That missing mass is thought to be dark matter, and much of it resides in the halo, forming a vast invisible reservoir that helps bind the galaxy together. The Milky Way is not a static shape. It slowly changes over time. Galaxies are dynamic, stars are born, stars die. Gas flows in and out. Gravity shapes and reshapes the structure. The Milky Way you see tonight is not exactly the Milky Way of 1 billion years ago, nor the one that will exist 1 billion years hence. The changes are slow, imperceptible on human timescales, but they're real. The galaxy is evolving, growing, responding to the forces acting on it. Gravity quietly organises everything into these large-scale forms. Behind all this structure, spiral arms, bulge, halo, disk, is gravity. Gravity pulls matter together, sets it spinning, flattens it into a disk, concentrates it into a bulge. Gravity holds stars in orbit, keeps gas clouds from dispersing, binds clusters together. It's the organising principle, the invisible hand shaping the galaxy, and it does all this quietly, without fanfare, just the patient, inexorable pull of mass on mass. Just one more small fact and then we drift. The galactic centre lies in the direction of the constellation Sagittarius. From Earth, if you look toward Sagittarius during the summer months, in the northern hemisphere, you're looking toward the heart of the Milky Way. The centre itself is hidden by dust, so you can't see it directly with visible light, but that direction is where the core lies, roughly 26,000 light-years away. It's a helpful anchor, a way to orient yourself when you look at the night sky. The centre is crowded with stars, gas and dust. The galactic centre is not a calm, empty place. It's a dense, energetic region where stars are packed closely together and where immense clouds of gas and dust swirl. The environment there is extreme by our standards. More radiation, stronger gravity, more frequent interactions between stars and clouds. It's the bustling downtown of the galaxy, contrasting sharply with the quieter suburbs where we reside. It's difficult to see directly in visible light because dust blocks the view. If you tried to observe the galactic centre with an ordinary telescope using visible light, you'd be disappointed. The view is obscured by intervening dust clouds, which absorb and scatter the light from the centre. This is why early astronomers, limited to visible light, had trouble understanding the galaxy's structure. They could see the Milky Way band, but the centre remained hidden. Infrared and radio observations help us see through dust. Fortunately, light comes in many forms, and some wavelengths pass through dust more easily than others. Infrared light, with its longer wavelength, can penetrate dust clouds that block visible light. Radio waves can do the same. By observing the galactic center in these wavelengths, astronomers have been able to map its structure, identify individual stars, and study the gas and dust there. It's a reminder that seeing isn't always about visible light. Sometimes you have to look in other ways. At the center is a supermassive black hole called Sagittarius A. This is one of the most striking discoveries in modern astronomy. At the very heart of the Milky Way, there's a black hole, not a small one formed from a single collapsing star, but a supermassive black hole with a mass about 4 million times that of the Sun. It's called Sagittarius A, or SEGR, just for short. The asterisk is part of the name, a convention from radio astronomy. This black hole is the anchor point of the galaxy, the gravitational center around which everything else orbits. A supermassive black hole can be calm for long periods. Despite its fearsome reputation, a black hole doesn't reach out and grab things. It just sits there, exerting gravity like any other mass. SGRA is relatively quiet at the moment. It's not actively consuming large amounts of material, so it's not blazing with radiation. Occasionally gas or a star might venture too close and fall in, producing a brief flare of energy, but much of the time the black hole is simply there, silent and still, a dense point of gravity. The center region has intense gravity because of all its mass. The combination of the black hole and the dense packing of stars creates a region of very strong gravity. Stars near the center orbit much faster than stars farther out. Some stars have been observed whipping around SGRA at a significant fraction of the speed of light, completing an orbit in just a few years, a stark contrast to the Sun's 200 million year orbit. That speed is a measure of the gravitational pull, a sign of how much mass is concentrated there. Stars near the center orbit rapidly compared with our neighborhood. If you could watch the galactic center over years or decades, you'd see stars moving noticeably against the background. This is unusual. Most stars are so far away that their motion is imperceptible over a human lifetime. But near SGRA, orbits are tight and fast, and astronomers have tracked individual stars moving in elliptical paths around the black hole. These observations have been crucial in confirming the black hole's existence and measuring its mass. The galactic center is far away, like a distant lighthouse you don't need to approach. It's worth pausing on this image. The galactic center is important, central to the galaxy's structure and dynamics, but it's also remote. You don't have to worry about it. Its gravity affects the large-scale motion of the galaxy, but from 26,000 light-years away, its influence on the solar system is negligible. It's a distant anchor, a point of reference, but not something that reaches into our local space. It can be thought of as the quiet hub of our galaxy's slow turning. The center is where the rotation is anchored, where the galaxy's mass is most concentrated. Everything orbits around it, layer upon layer, from the innermost stars whipping around in years to the outermost halo objects taking hundreds of millions of years. The center doesn't rush. It doesn't need to. It simply is, a focal point, a hub, the still point in the turning galaxy. Just one more small fact, and then we drift. The Milky Way's arms contain many regions where new stars form. The spiral arms are not just brighter because they contain more stars, they're brighter because they're actively making new stars. Star formation tends to happen in the arms because that's where gas clouds are compressed, where conditions are right for gravity to pull clouds into collapse. These regions are often marked by glowing nebulae, clouds of gas lit up by the ultraviolet light of young hot stars. Stars form when cold gas clouds collapse under gravity. Star formation is a process driven by gravity. A cloud of cold gas, often molecular hydrogen, sits in space. If a region within that cloud becomes dense enough, gravity begins to pull it together. As it collapses, it heats up, eventually becoming so hot and dense that nuclear fusion ignites in the core. A star is born. The process is slow, taking perhaps a few million years from the initial collapse to a stable, shining star, but the end result is the same, matter becoming light. These clouds are often called molecular clouds. Molecular clouds are the nurseries of stars. They're vast regions of space filled with gas and dust, cold enough that atoms combine into simple molecules, hence the name. Hydrogen molecules, H2, carbon monoxide, water, and many other molecules have been detected in these clouds. The cold temperatures and high densities make them ideal places for star formation. Some molecular clouds are enormous, containing enough material to form thousands or even millions of stars. Dust within clouds helps them cool and clump together. Dust plays a crucial role in star formation. The dust grains within a molecular cloud can absorb and re-radiate energy, helping the cloud lose heat. As the cloud cools, it becomes easier for gravity to pull it together. Without cooling, the cloud's internal pressure would resist collapse. Dust also provides surfaces where molecules can form, and it shields the interior of the cloud from disruptive radiation. In these ways, dust is not just an obstruction, it's a facilitator helping stars come into being. Star-forming regions can glow when nearby stars energize the gas. Once a few stars have formed within a cloud, especially if they're massive and hot, their radiation can ionize the surrounding gas, stripping electrons from atoms. The ionized gas glows, emitting light in specific colors determined by the elements present. These glowing regions are called emission nebulae, or H2 regions, ionized hydrogen regions. They're some of the most beautiful sights in the galaxy. Brilliant clouds of red, pink and blue, each one a sign that new stars have ignited and are lighting up their surroundings. Many bright nebulae are visible signs of star birth. The Orion Nebula, for example, is a famous star-forming region, easily visible to the naked eye as a fuzzy patch in Orion's sword. Within that nebula, stars are being born right now. Telescopes reveal young stars, still surrounded by the remnants of their birth clouds, and protostars still in the process of collapsing. These nebulae are dynamic, evolving. Over millions of years, the stars will disperse the remaining gas, and the nebula will fade, leaving behind a new cluster of stars. Starbirth is slow, more like a long dawn than a sudden flash. It's important to dispel any notion of star formation as a dramatic explosion. It's not. It's a gradual process. A cloud collapses over millions of years. The protostar grows, gathers mass, heats up. Eventually fusion begins, but even that is a gentle ignition, a slow ramp-up rather than a sudden burst. The star then settles onto what's called the main sequence, where it will spend most of its life steadily fusing hydrogen into helium. The whole process is patient, unhurried, like the galaxy itself. Some stars form in clusters, like neighborhoods turning on their lights together. Not all stars form in isolation. Often a single molecular cloud will give birth to dozens, hundreds, or thousands of stars at roughly the same time. These stars born together tend to remain gravitationally bound for at least a while, forming a star cluster. Open clusters, like the Pleiades, are examples of this. Groups of young stars still relatively close together, sharing a common origin. Over time, the cluster may disperse as stars drift apart, but for a time, they're a family, bound by gravity and shared history. Massive stars live shorter lives than small stars. This might seem counterintuitive. Surely a bigger star with more fuel would last longer. But it doesn't work that way. Massive stars burn their fuel much more quickly. They're hotter, brighter, and they fuse elements at a furious rate. A star with 10 times the mass of the Sun might live only a few million years, while a star with half the Sun's mass could shine for tens or even hundreds of billions of years. It's a trade-off. Brightness and brevity versus dimness and longevity. Small stars can shine steadily for extremely long times. The smallest stars, red dwarfs, are the tortoises of the stellar world. They're dim, cool, and they burn their hydrogen fuel so slowly that they can last for trillions of years, far longer than the current age of the universe. None of these stars has ever died of old age because they simply haven't had time. They'll outlast nearly everything, quiet and persistent, shining faintly into the deep future. Just one more small fact, and then we drift. Because we're inside the Milky Way, mapping it is like mapping a forest from within. Imagine standing in the middle of a vast forest and trying to draw a map of it. You can see the trees around you, you can measure distances to nearby landmarks, but much of the forest is hidden by the trees themselves. You have to infer the overall shape from limited views, from patterns and clues. That's the challenge astronomers face with the Milky Way. We can't step outside to get a clear view, so we have to piece together the structure from observations made from our single vantage point. Astronomers use many wavelengths of light to study the galaxy. Visible light is useful, but it's only part of the story. Different wavelengths reveal different aspects of the galaxy. Radio waves show where cold hydrogen gas is concentrated. Infrared light reveals stars hidden by dust and shows the thermal glow of dust itself. X-rays highlight high-energy processes, like gas heated to extreme temperatures. By combining observations across the electromagnetic spectrum, astronomers build a more complete picture of the Milky Way's structure and contents. Radio waves can travel through dust more easily than visible light. This is one of the key advantages of radio astronomy. Dust that would block or scatter visible light is largely transparent to radio waves. This means astronomers can use radio telescopes to observe the galactic center, star-forming regions deep within molecular clouds and other obscured parts of the galaxy. Radio observations have been essential in mapping the spiral arms and understanding the distribution of gas. Hydrogen gas emits a radio signal used to map large structures. Neutral hydrogen, hydrogen that hasn't been ionized, emits radio waves at a very specific wavelength, about 21 centimeters. This emission comes from a subtle quantum transition in the hydrogen atom. Because hydrogen is the most abundant element in the universe, this 21 centimeter line is a powerful tool. By observing it, astronomers can map where hydrogen gas is located throughout the galaxy, tracing out the spiral arms and the large-scale structure of the disk. Infrared light can reveal stars hidden by dust. Dust absorbs visible light but re-radiates that energy in the infrared. So infrared telescopes can see through dusty regions and detect the stars within. Infrared surveys of the Milky Way have uncovered vast numbers of stars, including many cool dim stars that would be nearly invisible in visible light. These observations have helped astronomers understand the true stellar population of the galaxy. Star motions help us understand the galaxy's mass distribution. By measuring how fast stars are moving and in what orbits, astronomers can infer how much mass is present and where it's located. This is similar to how we can deduce the sun's mass by watching how the planets orbit. If you know how fast something is moving and the radius of its orbit, you can calculate the mass it's orbiting. Applied across the galaxy, this technique reveals the distribution of matter, both visible and dark. If stars move faster than expected, it hints at unseen mass. One of the big surprises in studying galaxies, including the Milky Way, was that stars in the outer regions move faster than they should if only the visible matter were present. According to Newton's laws, stars farther from the center should orbit more slowly, just as outer planets in the solar system orbit more slowly than inner ones. But that's not what we see. Stars far from the galactic center orbit at roughly the same speed as those closer in. This suggests there's additional mass we can't see, providing extra gravitational pull. This is one reason dark matter is included in Milky Way models. To explain the observed motions, astronomers add dark matter to their models. Dark matter doesn't emit light, doesn't interact via the electromagnetic force, but it has mass and therefore gravity. By including a large halo of dark matter surrounding the galaxy, models can match the observed rotation curves. The nature of dark matter is still one of the biggest mysteries in physics, but its presence in the Milky Way is strongly suggested by the evidence. We also map the galaxy by measuring distances to star clusters and special variable stars. Distance measurement is crucial in astronomy, and it's not always easy. For nearby objects, parallax, the apparent shift of a star's position as Earth orbits the Sun, can give direct distance measurements. For more distant objects, astronomers use standard candles, objects with known intrinsic brightness. Certain types of variable stars, like Cepheids, have a relationship between their pulsation period and their luminosity. By measuring the period, astronomers can deduce the luminosity, compare it to the observed brightness, and calculate the distance. Over time, these measurements build a calm, detailed picture of our home. Each observation is a piece of the puzzle. Each distance measurement, each spectrum, each image adds to the understanding. It's slow work, requiring patience and precision, but the result is a growing map of the Milky Way, its size, shape, structure, and contents. And that map is not static. It's constantly refined as new data comes in, as techniques improve, as we learn more about the galaxy we live in. Just one more small fact, and then we drift. Star clusters are groups of stars bound together by gravity. Within the vast expanse of the Milky Way, stars sometimes gather into clusters, tightly knit groups where stars are much closer together than average. Gravity holds these clusters together, resisting the forces that would otherwise pull them apart. Clusters are laboratories for studying stellar evolution because all the stars in a cluster were born at roughly the same time and from the same material, making it easier to compare them. Some clusters are young and still close to their birth clouds. Open clusters like the Pleiades or the Hyades are relatively young by astronomical standards, often just a few 100 million years old or less. They're often still associated with the nebulae from which they formed, or at least located in regions rich with gas and dust. These clusters are loose, with stars spread over many light years, and they contain stars of various masses, including hot blue massive stars that haven't yet burned out. Others are ancient and live, in the halo. Globular clusters are very different. They're old, dense and spherical, containing tens of thousands to millions of stars packed into a volume just tens of light years across. Globular clusters orbit in the galactic halo, often far from the disk. Their stars are ancient, typically 10 billion years or older, and they're metal poor, meaning they formed when the universe had fewer heavy elements. Globular clusters are relics of the early galaxy, survivors from a time when the Milky Way was still taking shape. Globular clusters are dense, round collections of very old stars. Imagine a spherical swarm of stars, so densely packed that near the centre, stars might be separated by just light days rather than light years. If you could stand on a planet near the centre of a globular cluster, the night sky would be astonishing, filled with thousands of bright stars, possibly enough to cast significant light even at night. Globular clusters are gravitationally stable. They've existed for billions of years and will likely persist for billions more. Open clusters are looser groups, often younger, found in the disk. Open clusters are scattered throughout the Milky Way's disk, especially in the spiral arms where star formation is active. They're less tightly bound than globular clusters, and over time, many of them will disperse as their stars drift apart. Tidal forces from the galaxy can pull stars away, and close encounters with molecular clouds can disrupt the cluster. But while they last, open clusters are beautiful, a reminder that stars are not always solitary. Our Sun may have been born in a cluster long ago. This is an intriguing possibility. Most stars form in clusters, so it's likely the Sun did too. Early in its life, the Sun would have been part of a group of sibling stars, all born from the same molecular cloud. But over 4.5 billion years, those siblings have scattered, drifting apart as they orbit the galaxy. Some might still be out. There, stars with the same chemical composition, the same age, but now separated by vast distances. Astronomers have searched for these solar siblings, but identifying them is difficult because so much time has passed. Over time, clusters can disperse as stars drift apart. Even bound clusters don't last forever. Gravitational interactions, both internal and external, can gradually eject stars from the cluster. Each encounter, each pass near another star or a massive cloud, changes the orbit slightly. Over millions or billions of years, these changes accumulate. Open clusters in particular often disperse within a few 100 million years. Globular clusters last longer because they're more tightly bound, but even they can lose stars over time. The galaxy is full of moving groups that share a common origin. Even after a cluster has dispersed, the stars that once belonged to it continue to share certain characteristics. They have similar motions through space, similar velocities, similar trajectories, because they started out together. They may also have similar chemical compositions, similar ages. Astronomers can identify these moving groups by looking for stars with correlated motions. It's like seeing a group of people walking in different directions but all starting from the same point. You can trace back their paths and infer that they were once together. Even when stars separate, their shared motion can remain as a faint signature. This shared motion is a kind of fossil record, a trace of the past. By studying it, astronomers can learn about the history of star formation in the Milky Way, about how clusters form and dissolve, about the dynamical processes that shape the galaxy. It's a subtle detective work, piecing together history from the faintest of clues. In this way, the Milky Way keeps gentle traces of its own history. The galaxy is not a blank slate. Its current structure reflects its past, the mergers it has undergone, the star formation events that have occurred, the clusters that have formed and dispersed. Every star, every orbit, every chemical abundance is a piece of the story, and by studying these traces, astronomers can read that story, learning how the Milky Way came to be and how it continues to evolve. Just one more small fact, and then we drift. The Milky Way formed long ago from smaller pieces coming together. Galaxies don't spring into existence fully formed. They grow, built up over time as gas, stars, and dark matter accumulate under gravity's pull. The early universe was smoother, more homogeneous, but tiny density fluctuations seeded the growth of structure. Over millions and billions of years, those fluctuations grew, pulling in more matter, forming the first stars, the first galaxies. The Milky Way is one result of that process, a galaxy that has been assembling itself for most of the age of the universe. Galaxies can grow by merging with other galaxies. One of the key processes in galaxy evolution is merging. When two galaxies come close together, gravity can pull them into a dance. They orbit each other, slowly spiraling inward, until eventually they merge into a single, larger galaxy. This process can reshape the galaxies involved, triggering star formation, disrupting disks, and mixing stellar populations. It's a dramatic event on cosmic scales, though even a galaxy merger unfolds over hundreds of millions of years. Evidence suggests the Milky Way has absorbed smaller galaxies over time. The Milky Way hasn't grown in isolation. It has interacted with and consumed smaller galaxies. We see evidence of this in the form of stellar streams, long, thin ribbons of stars stretched across the sky. These streams are the remnants of smaller galaxies that ventured too close to the Milky Way and were torn apart by tidal forces. The stars from these smaller galaxies now orbit within the Milky Way's halo, though they retain a memory of their origin in their correlated positions and motions. Some star streams in the halo may be remnants of past mergers. The Sagittarius dwarf elliptical galaxy, for example, is currently in the process of being pulled apart by the Milky Way. Its stars are being stretched into streams that wrap around the galaxy. Over time, these stars will be fully assimilated, becoming part of the Milky Way's halo. This process has likely happened many times in the galaxy's history, each merger adding stars, gas, and mass to the Milky Way. Mergers are not always violent looking from afar. They can be slow, graceful reshaping. The word collision might evoke images of destruction, but galaxy mergers are not like car crashes. The distances between stars within a galaxy are so vast that even when two galaxies merge, direct collisions between stars are extremely rare. Instead, the galaxies pass through each other, their shapes distorted by gravity, their orbits altered, their structures gradually blending. From a distance, a galaxy merger might look like two clouds of stars flowing together, mixing and settling into a new form. The Milky Way is part of a group of galaxies called the Local Group. The Milky Way doesn't exist in isolation. It's part of a small cluster of galaxies, a collection of about 50 or so galaxies bound together by gravity. The Local Group spans several million light-years and is dominated by two large spiral galaxies, the Milky Way and Andromeda. The rest are mostly small dwarf galaxies, each with its own history and structure. The Local Group is our cosmic neighbourhood, the cluster of galaxies closest to home. One of our large neighbours is the Andromeda Galaxy. Andromeda, also known as M31, is the nearest large spiral galaxy to the Milky Way, about 2.5 million light-years away. It's bigger than the Milky Way, with more stars and a slightly larger disk. On a dark night, Andromeda is visible to the naked eye as a faint, fuzzy patch in the constellation of the same name. It's one of the most distant objects you can see without a telescope, and it's heading our way. Over very long timescales, the Milky Way and Andromeda are expected to interact. Observations of Andromeda's motion show that it's approaching the Milky Way. In fact, the two galaxies are on a collision course, but collision is a strong word for an event that won't happen for billions of years. Current estimates suggest that the Milky Way and Andromeda will begin to interact in about 4 billion years. They'll undergo a slow, complex dance, orbiting each other, pulling on each other, eventually merging into a single larger galaxy. This is a distant future event, not a near worry. By the time this merger happens, the Sun will be nearing the end of its life, expanding into a red giant. Earth, if it still exists, will be uninhabitable. The timescales involved are so vast that this merger is not something to fear, or even to think about in practical terms. It's just a reminder that the universe is dynamic, that galaxies evolve, that even structures as vast as the Milky Way are part of ongoing change. The universe is patient. Most of its stories move on deep timescales. This is worth repeating because it's so counter to human experience. We live in days and years. We see change on those scales. but the universe operates on timescales of millions, billions, even trillions of years. Stars are born and die over millions of years. Galaxies merge over billions. The universe itself is about 14 billion years old, and it will continue for untold eons. There's no rush, no urgency. Everything unfolds at its own pace, slow and steady, governed by the laws of physics and the patience of time. Just one more small fact, and then we drift. Light takes time to travel, even though it's extremely fast. Light moves at about 300,000 kilometers per second, the fastest speed in the universe. Nothing with mass can reach that speed, and even light, massless as it is, takes time to cross distances. From the Sun to Earth, light takes about 8 minutes. From the nearest star, over 4 years. From the far side of the Milky Way, 100,000 years. This delay is fundamental to how we perceive the universe. When you look at stars, you see them as they were, not as they are right now. This is one of the most poetic aspects of astronomy. The light that enters your eye tonight left its star long ago. Perhaps years, perhaps centuries, perhaps millennia. In a real sense, looking at the night sky is looking into the past. The stars you see are not as they are now, but as they were when their light began its journey, and there's no way around this. The speed of light is finite, and distance imposes delay. Some starlight began its journey long before you were born. If you look at a star 1,000 light years away, the light you see left that star 1,000 years ago. If you're seeing it tonight, it began its journey in the year 1026. Empires have risen and fallen in that time. Generations have come and gone, and all the while that light was travelling through space, carrying information about a star as it was a millennium ago. The Milky Way band, you imagine, is made of countless travel times layered together. Every star in that band is at a different distance, and so the light from each one has been travelling for a different amount of time. The combined glow is a patchwork of different eras, all arriving at your eye in the same instant. It's a mosaic of time, a visual history of the galaxy compressed into a single view. You're seeing the galaxy not as it is, but as it has been across a span of time. The atoms in your body were formed in older generations of stars. This is one of the most profound connections between you and the Milky Way. The hydrogen in your body dates back to the Big Bang, but most other elements, carbon, nitrogen, oxygen, phosphorus, calcium, iron, were forged in the cores of stars. Those stars lived, burned, and eventually died, some in quiet fade-outs, others in spectacular supernova explosions. In dying, they released their enriched material into space, where it mixed with gas clouds and eventually became part of new stars, new planets, and new life. Elements like carbon, oxygen, and iron were forged in stellar interiors. Stars are nuclear furnaces. In their cores, hydrogen fuses into helium. In more massive stars, helium fuses into carbon and oxygen. The process continues up the periodic table, building heavier and heavier elements until you reach iron. Iron is the end point. Fusing iron requires energy rather than releasing it, so fusion stops there. When a massive star explodes as a supernova, the explosion creates even heavier elements and scatters all that enriched material into space. Over time, that material becomes part of new stars, planets, and eventually living things. In that sense, your body is part of the Milky Way's ongoing recycling. The galaxy is a vast recycling system. Stars form, leave, die, and their material is reused. The atoms in your bones, your blood, your brain have been through this cycle, perhaps multiple times. They've been inside stars, blown out in stellar winds or supernova explosions, drifted through interstellar space, condensed into a molecular cloud, formed the sun and earth, and eventually became part of you. You're made of star stuff, as Carl Sagan famously said. You're the Milky Way, aware of itself. The galaxy turns quietly, whether you watch it or not. This is a comforting thought. The Milky Way doesn't need your attention. It existed long before you, and it will continue long after. Its rotation, its star formation, its slow evolution, all of these proceed independently. You can observe, you can learn, you can marvel, but the galaxy is indifferent. It simply is, doing what it does, following the laws of physics, existing on timescales that dwarf your life. Rest is also a kind of orbit, returning again and again to stillness. This is a gentle metaphor, a way to bring the cosmic back to the personal. Just as the Sun orbits the galactic center, returning to the same approximate region every 200 million years, you return to rest every night. You orbit through wakefulness and sleep, activity and stillness, and in that return there's a rhythm, a pattern, a sense of belonging to cycles larger than yourself. Tonight you don't have to chase any thought, because you're already held inside a slow, rotating home of stars. This is the final fact, and it's meant to release you. You don't have to hold on to any of this. You don't have to remember or understand or do anything. You're already part of the Milky Way. You're already moving through space, already connected to the galaxy by the atoms in your body and the motion of your planet. You're already home. And in that knowledge, you can let go, let your thoughts drift, and simply rest. Just one more small fact, and then we drift. Even in stillness, the universe moves, gently. This is the essence of it all. You lie still, but you're moving. Earth spins. Earth orbits the sun. The sun orbits the galaxy. The galaxy moves relative to others. Motion is everywhere, but it's quiet, smooth, not something you feel. It's a background hum, a slow dance that requires nothing from you. You can be still, and the universe will carry you. Let the Milky Way keep turning. It doesn't need your help. It doesn't need your consciousness or your awareness. It turns because it must, because gravity and momentum and the structure of space-time dictate that it does. And in that turning, there's a stability, a reliability. The galaxy has been turning for billions of years. It will continue. You can trust that, and let your thoughts drift with it. Imagine your thoughts as small, light things carried along by the gentle current of the galaxy's rotation. They don't need to go anywhere specific. They don't need to resolve into decisions or conclusions. They can just drift, like dust motes in a beam of light, like stars in a slow orbit. Let them go where they will, and don't hold on, until you don't need thoughts at all. This is the final invitation. There comes a point in rest where even thoughts are too much, where the mind quiets to near silence. That's where sleep begins, in that space where thoughts fade and awareness softens. You don't need to force it, just allow it, the way you allow the galaxy to turn. Let your thoughts thin out, become less frequent, less insistent, until there's only the soft, quiet darkness and the sense of being held safe inside this vast, slow home of stars. Breathe in, breathe out. The Milky Way turns, you rest, and that is enough. The next story is about to begin. Please relax and enjoy. A forest is an ecosystem where trees are the main builders of the environment. When you think about a forest, you might picture tall trunks and leafy branches, but what makes a forest truly a forest is the way trees shape everything around them. They create the conditions that allow other life to flourish. They determine where light falls and where shadows gather. They influence the temperature, the moisture in the air, even the way wind moves through space. A forest isn't just a collection of trees standing near each other. It's a living architecture, built slowly over time, where trees are the architects and engineers of an entire world. Forests create their own rooms of shade, windbreak and moisture. Step inside a forest on a bright summer day, and you'll notice the change immediately. The light becomes softer, filtered through layers of leaves. The air feels different against your skin, often cooler and more humid than the open field you just left behind. The wind that might have been rushing across grassland suddenly quiets to a gentle stirring. These aren't accidents. These are the effects of the forest building its own interior climate, its own set of conditions that differ from the world outside. The trees themselves create these rooms, these chambers of particular temperature and light, and in doing so they make space for life that couldn't exist in harsher, more exposed places. The air under a canopy is often calmer because leaves slow the wind. Wind moves freely across open ground, gaining speed, pushing against everything in its path. But when wind meets a forest, it encounters resistance. The leaves, thousands upon thousands of them, each catch a bit of the moving air. They flex and flutter, absorbing the wind's energy. The branches sway, giving way to pressure but also dissipating it. By the time wind has passed through the outer edge of a forest and moved deeper into the canopy, much of its force has been spent. The result is a kind of quietness in the air itself, a stillness that exists not because there's no movement, but because the movement has been gentled, softened, turned into something less forceful and more subtle. Forest floors are quieter because plants and soil absorb sound. It's not just the air that feels different in a forest. Sound behaves differently too. When you walk through an open field and call out, your voice carries. It bounces off hard surfaces, travels far. But in a forest, sound seems to settle and fade more quickly. This happens because the forest is full of soft, irregular surfaces. The leaf litter on the ground is spongy and porous. The moss on tree trunks is soft and textured. The layers of vegetation at different heights all catch sound waves and absorb them rather than reflecting them back. Even the soil itself, often rich and full of air pockets and organic matter, dampens sound. The result is a place where noise doesn't echo and carry the way it does in harder landscapes. Everything is muffled, quieted, turned down to a gentler volume. Forests can feel cooler in the day and milder at night than open fields. This temperature effect is one of the most noticeable things about spending time in a forest. On a hot afternoon, the shade alone provides relief, but there's more happening than just blocked sunlight. The trees are actively cooling the air through their life processes, releasing water vapor that carries heat away. The soil stays cooler because it's protected from direct sun. At night, the situation reverses in an interesting way. While open fields can become quite cold as heat radiates away into a clear sky, the forest canopy acts like a blanket, holding some warmth close to the ground. The temperature swings are smaller, more moderate. Day and night still happen, hot and cold still exist, but the extremes are softened. The forest creates a climate that's more stable, more even, more gentle in its changes. Just one more small fact and then we drift. Trees grow from the tips of shoots and roots, adding length each season. If you've ever watched a tree over many years, you might have noticed something interesting. The lowest branch doesn't rise higher as the tree gets taller. That first branch, the one that formed when the tree was young, stays at the same height above the ground for the tree's entire life. This is because trees don't grow the way animals do, adding size all over. Instead, trees grow from specific points, from the tips of their branches and the ends of their roots. Each spring, new cells form at these growing tips, pushing the branch a bit longer, extending the root a bit further. The trunk gets wider over time, but its length comes from new growth at the top, from the terminal bud that adds another season's worth of height. This pattern of growth focused at the tips is part of why trees can reach such remarkable heights. They're always reaching upward, always extending, but always from the same growth points. Many trees add new wood in a thin layer just under the bark. While the tips of branches are pushing outward and upward, something else is happening along the trunk and larger branches. Just beneath the protective bark, there's a thin layer of living cells called the cambium. This layer is where new wood forms. Throughout the growing season, the cambium produces new cells on its inner surface, and these cells become wood, adding to the tree's diameter. It's a slow process, invisible from day to day, but steady. Each year, this thin layer of growth adds another ring to the tree's structure. The tree becomes slightly wider, slightly more substantial, its trunk growing in girth even while its height comes from those tips reaching skyward. This dual system of growth, length from the tips and width from the cambium, is how trees build their remarkable structures over time. Growth rings form when wood grows fast in spring and slower later in the season. If you've ever looked at a stump or a cut log, you've probably seen the rings. They're one of the most recognizable features of wood, these concentric circles that mark the passage of years. But what creates these rings isn't something the tree does deliberately. It's simply a record of how the tree grew at different times. In spring, when water is often plentiful and days are lengthening, the tree grows quickly. The cells it produces are larger, with thinner walls, optimized for rapid expansion. This wood is lighter in colour and less dense. Later in the season, as growth slows, the tree produces cells that are smaller and more tightly packed, with thicker walls. This wood is darker and denser. The contrast between the light spring wood and the dark summer wood creates a visible line, a boundary between one year's growth and the next. These rings aren't decorative, they're functional, a side effect of the tree's response to seasonal changes. Wide rings often mean easier growing conditions that year. When you look at tree rings, you're looking at a history written in wood. The width of each ring tells you something about what that year was like for the tree. A wide ring suggests that the tree had what it needed. Perhaps that year brought good rainfall, distributed throughout the growing season. Perhaps the temperature was favourable, not too hot, not too cold, allowing for steady growth. Perhaps the tree wasn't competing as intensely with neighbours for light and nutrients. Whatever the specific reasons, a wide ring is generally a sign that the tree could invest energy in growth, that conditions allowed it to add substantial girth during that season. These wider years might be scattered through the tree's life, or they might cluster together during a period of particularly good conditions. Each ring is a record, a memory preserved in wood. Narrow rings often mean a tougher year, less water, more stress, or colder weather. Conversely, a narrow ring suggests that the tree faced challenges during that growing season. Perhaps a drought limited the water available for cell production. Perhaps an unseasonably cold summer slowed the tree's metabolism. Perhaps insect damage or disease reduced the tree's ability to photosynthesize effectively. Perhaps competition with neighbouring trees intensified, leaving less light and nutrients to go around. The tree still grew, still added wood, but it did so more conservatively, producing fewer cells, adding less girth. These narrow rings can reveal periods of hardship in the tree's life, years when simply surviving took most of the tree's resources. Over the decades or centuries of a tree's life, the pattern of wide and narrow rings creates a unique record, a personal history encoded in the structure of the wood itself. Bark is a tree's protective outer layer against injury and drying. While the wood inside grows and changes, the outer surface of the tree needs protection. Bark serves this function, acting as armour and shield. It protects the living tissues, beneath from physical damage, whether from animals, falling branches, or other impacts. It helps prevent the tree from losing too much water through evaporation, keeping the vital cambium layer from drying out. It can provide some insulation against temperature extremes, both hot and cold. Bark isn't alive in the same way the wood beneath it is. It's made of dead cells, but those dead cells serve an important purpose. They're expendable, able to take damage while protecting the living layers below. As a tree grows wider, its bark must crack and stretch to accommodate the expanding trunk, creating the textured patterns we see on different species. Some bark is thick for fire protection, some is thin for fast growth. Different trees have evolved different bark strategies depending on where they live and what challenges they face. In regions where fire is common, some trees have developed remarkably thick bark, sometimes several inches deep. This bark can insulate the living tissues beneath from the heat of a fire, allowing the tree to survive burns that would kill a thin-barked tree. Species like ponderosa pine or cork oak have evolved this protective adaptation. Other trees, particularly those in cooler, wetter climates where fire is rare, often have much thinner bark. These trees invest less energy in protective bark and more in rapid growth, getting taller faster, reaching light more quickly. The thickness of bark is a trade-off, a choice made over evolutionary time about how to allocate resources and what dangers to prioritize protecting against. Leaves gather sunlight to make sugars through photosynthesis. The leaves of a tree are perhaps its most remarkable organs, the places where the tree captures energy from sunlight and turns it into something it can use. This process, photosynthesis, is so fundamental to life on Earth that it's easy to take for granted, but it's worth slowing down to consider what's actually happening. A leaf is essentially a solar panel, but instead of generating electricity, it's manufacturing food. The broad, flat surface of the leaf is designed to intercept as much light as possible. Inside the leaf, in structures called chloroplasts, molecules of chlorophyll absorb the light energy. This energy is then used to power a series of chemical reactions that transform simple raw materials into complex sugars. It's a quiet miracle happening in every leaf, every moment the sun is shining. Photosynthesis turns sunlight, water, and carbon dioxide into energy-rich food. The raw materials for photosynthesis are remarkably simple. Water comes up from the soil through the roots and wood of the tree. Carbon dioxide comes from the air, entering the leaf through tiny pores called stomata. Sunlight provides the energy. From these three simple ingredients, the leaf manufactures glucose, a sugar molecule that the tree can use for energy or convert into other compounds it needs. As a byproduct of this process, the leaf releases oxygen back into the air. This exchange, carbon dioxide in and oxygen out, is one of the reasons forests are so important for maintaining the atmosphere's composition. But for the tree itself, photosynthesis is simply how it eats. Unlike animals, which must find and consume food, trees make their own food from sunlight, water and air. It's a quieter, slower way of feeding, but remarkably effective. Tree roots anchor the trunk and also gather water and minerals. Below ground, invisible to us as we walk through a forest, another system is at work. The roots of a tree spread outward and downward, creating a mirror image of the branches above. These roots serve multiple functions. Obviously, they anchor the tree, keeping it stable against wind and the weight of its own crown. But they're also the tree's water and mineral acquisition system. The soil holds water in the spaces between particles, and it contains dissolved minerals that the tree needs for growth, things like nitrogen, phosphorus, potassium, and many others. The roots must find this water and these minerals, absorb them, and transport them upward to the rest of the tree. It's a challenge, because soil is not uniform. Some areas have more water, some have more minerals. The roots must explore, must grow toward resources, constantly adjusting their growth pattern in response to what they find. Fine roots do most of the absorbing, like soft threads in soil. When you picture tree roots, you might imagine the large woody roots visible at the base of the trunk or sometimes exposed on the surface. These structural roots are important for anchoring and for transporting water and nutrients, but they're not where most of the actual absorption happens. Instead, the tree produces enormous numbers of fine roots, tiny structures sometimes thinner than a thread. These fine roots grow and die and regrow constantly, exploring the soil in detail. Their small size gives them a large surface area relative to their volume, making them efficient absorbers. Many of these fine roots are also covered in even tinier root hairs, single cells that extend outward, further increasing the surface area in contact with soil. These fine roots and root hairs are where water and minerals actually enter the tree, crossing from the soil into the living tissue. They're delicate and short-lived but essential. Trees move water upward through tiny tubes in their wood. Once water enters the roots, it faces a significant challenge. It needs to move upward, sometimes hundreds of feet upward in tall trees, all the way to the topmost leaves. The tree has no pump, no heart pushing the water along. Instead, it relies on the structure of wood itself. Wood contains long, thin tubes called xylem vessels. These tubes are made of dead cells stacked end to end, their end walls dissolved away to create continuous pipes, from roots to leaves. Water moves through these tubes, rising against gravity. The mechanism that allows this is elegant and relies on the physical properties of water itself. Water molecules cling to each other through hydrogen bonding, a phenomenon called cohesion. They also cling to the walls of the xylem tubes, a phenomenon called adhesion. These properties, combined with the pull created by evaporation at the leaves, allow water to rise in an unbroken column from soil to sky. Water can rise because it clings together and pulls upward as it evaporates from leaves. At the top of the tree, in the leaves, water evaporates from the moist surfaces inside the leaf and exits through the stomata into the air. This process, called transpiration, creates a kind of suction. As water molecules evaporate from the leaf, they pull on the water molecules below them, which are held in the xylem tubes. Because water molecules are strongly cohesive, clinging to each other, this pull is transmitted down the entire column of water in the xylem, all the way to the roots. More water is then pulled into the roots from the soil to replace what was lost at the top. It's like a very slow, very long straw, except the suction comes from evaporation rather than breathing, and the liquid pulls itself up rather than being pushed. This transpiration stream is continuous during daylight hours throughout the growing season, moving vast quantities of water from soil to air through the tree. Many trees rest in winter by slowing growth and dropping leaves. The seasons impose a rhythm on tree life, particularly in temperate regions where winter brings cold temperatures and often frozen soil. For deciduous trees, those that lose their leaves in autumn, winter is a time of dormancy. Growth stops or slows to almost nothing. The tree enters a kind of suspension, conserving energy, waiting. Dropping leaves before winter serves several purposes. Leaves are vulnerable to cold and frost. They also continue to lose water through transpiration as long as they're present, but in winter, frozen soil makes it hard for roots to replace that lost water. A tree trying to maintain leaves through winter in a cold climate would risk desiccation, drying out despite being surrounded by ice and snow. By dropping its leaves, the tree reduces its water loss to minimal levels, retreating into itself, enduring the harsh season in a more protected state. Evergreen trees keep leaves longer, replacing them gradually instead of all at once. Not all trees follow the deciduous strategy. Evergreens, including most conifers and some broadleaf trees, take a different approach. These trees have leaves or needles that are tougher, more resistant to cold and desiccation. The leaves are often coated with a waxy layer that reduces water loss. They have smaller surface areas, which also helps minimize water loss. Instead of dropping all their leaves at once in autumn, evergreens replace leaves gradually throughout the year or over several years. At any given time, the tree has a full complement of leaves, but individual leaves are at different stages of their life cycle. Some are brand new, some are middle-aged, some are nearing the end of their functional life and will soon be shed. This strategy allows evergreens to photosynthesize whenever conditions permit, even in winter on warm days. They don't have to regrow their entire leaf canopy each spring. The trade-off is that their leaves are more expensive to make and maintain, but in certain environments, this trade-off is worthwhile. Just one more small fact, and then we drift. Leaves look green because chlorophyll reflects green light. The green colour of leaves is so familiar that we rarely stop to think about what causes it. Light from the sun contains all the colours of the visible spectrum. When this light hits a leaf, the chlorophyll molecules inside the leaf absorb most of the blue and red light, using that light's energy for photosynthesis. But green light is mostly reflected back, bouncing off the leaf rather than being absorbed. Our eyes receive this reflected green light, and we perceive the leaf as green. The green colour is, in a sense, the leftover light, the wavelengths that the chlorophyll doesn't use. This is why leaves appear green to us. The colour we see is the colour the leaf isn't using for energy. It's a simple physical phenomenon, but one that has painted much of our planet in shades of green for hundreds of millions of years. In autumn, chlorophyll breaks down, revealing other pigments. As days shorten and temperatures cool in autumn, deciduous trees begin preparing for winter. One of the first steps is to break down the chlorophyll in their leaves. Chlorophyll is complex and contains valuable nitrogen that the tree can reabsorb and store in its branches and trunk for use next spring. As the chlorophyll breaks down and is withdrawn from the leaf, the green colour fades, but leaves contain other pigments too, pigments that were there all along but were masked by the overwhelming presence of chlorophyll. These other pigments now become visible. The leaf, still attached to the tree but no longer functioning in photosynthesis, reveals colours that were hidden all summer long. This is the beginning of autumn colour, not a new development, but an uncovering, a revelation of what was always present but concealed. Yellows and oranges come from pigments that were there all along. The yellow and orange colours of autumn leaves come from pigments called carotenoids. These are the same compounds that make carrots orange and egg yolks yellow. In leaves, carotenoids play a supporting role during the summer, helping with photosynthesis and protecting the leaf from excess light energy. But they're always overshadowed by the abundant chlorophyll, which is much more intense in colour. When the chlorophyll breaks down in autumn, the carotenoids remain for a time, and their yellow and orange hues become apparent. The leaf hasn't created these colours in response to fall, it simply stopped producing the green that covered them. Different species have different amounts and types of carotenoids, which is why some trees turn brilliant yellow, while others show softer gold or orange tones. The colours were always there, just hidden, waiting for autumn to reveal them. Some reds form when sugars get trapped in leaves under cool, bright conditions. The red and purple colours of autumn are slightly different in origin from the yellows and oranges. These colours come from pigments called anthocyanins, and unlike carotenoids, anthocyanins are often newly created in autumn. They form when sugars become concentrated in leaves during cool nights and bright days. The cool temperatures slow the movement of sugars out of the leaf, while the bright sunshine continues to promote photosynthesis, creating more sugars. These accumulated sugars can lead to the production of anthocyanins. Scientists are still studying exactly why trees do this, but one theory is that anthocyanins may help protect the leaf, while the tree is still withdrawing valuable nutrients from it, acting as a kind of sunscreen against light damage. The intensity of autumn reds can vary greatly from year to year depending on weather conditions. Cool nights and sunny days create the most spectacular red displays, while warm, cloudy autumns produce more muted colours. Dropping leaves can help trees avoid winter water loss. The fall of leaves is a carefully orchestrated process. At the base of each leaf stem, in the spot where the leaf attaches to the branch, the tree forms a special layer of cells called the abscission layer. This layer is designed to separate cleanly, allowing the leaf to detach without leaving a wound that might let in disease or pests. As autumn progresses, the tree seals off the connection between the leaf and the branch, forming a protective layer over the spot where the leaf will fall. Eventually, the leaf is held on only by a few remaining strands of tissue. A gust of wind or the weight of rain is enough to complete the separation, and the leaf falls. What remains on the branch is a leaf scar, a small mark where the leaf once was, protected and sealed against the coming winter. The tree has successfully withdrawn most of the valuable nutrients from the leaf, broken it down, reabsorbed what it could use, and discarded what remained. Leaf litter becomes a blanket that protects soil from drying and erosion. Once on the ground, fallen leaves begin a new phase of their existence. They form a layer over the soil, a loose blanket that provides several benefits to the forest ecosystem. This layer of litter helps protect the soil from direct rainfall, which can compact bare soil and wash away particles. It reduces evaporation from the soil surface, helping to maintain moisture levels. In winter, the leaf litter provides some insulation, moderating temperature swings in the upper soil layers. The litter also becomes habitat. Countless small organisms live in and under leaf litter, from insects to spiders to millipedes. These creatures find shelter, moisture, and food in the decaying leaves. The leaf litter is not waste, it's a resource, a gift from the canopy to the forest floor, and it will continue to contribute to the forest ecosystem as it slowly breaks down. Decaying leaves return nutrients to the ground like slow-release food. Over the months and years following their fall, leaves gradually decompose. Fungi and bacteria colonize the dead tissue, breaking down the complex molecules that make up the leaf structure. Larger organisms, from earthworms to beetle larvae, consume the decaying leaves, fragmenting them into smaller pieces. Gradually, the recognizable leaf shape disappears. The material becomes part of the soil, mixing with mineral particles contributing organic matter. As this decomposition happens, the nutrients that were once part of the living leaf become available again. Nitrogen, phosphorus, potassium, and many other elements are released, back into the soil in forms that plant roots can absorb. The tree that dropped the leaves may well take up some of these recycled nutrients through its own roots. The forest operates as a cycle, with nutrients moving from soil to tree to leaf to litter, and back to soil again. It's a closed loop, efficient and elegant with very little waste. Some trees time their leaf out using temperature and day-length cues. When spring arrives, trees face the challenge of knowing when to break dormancy and begin growing again. Start too early, and a late frost can damage tender new leaves. Start too late, and the tree misses valuable growing time. Different species use different strategies to time their spring leaf out. Some trees primarily respond to accumulated warmth, essentially counting warm days until they reach a threshold that triggers bud break. Others are more sensitive to day length, using the increasing hours of daylight as their signal that spring has truly arrived. Many trees use a combination of cues, requiring both sufficient warmth and appropriate day length before they'll commit to leafing out. This is why, in a given forest, different species often leaf out at different times. Each has its own set of requirements, its own calculation of when the risk of frost is low enough, and the benefit of early growth high enough to justify breaking dormancy. Buds are tiny packed futures, leaves and flowers waiting in a protective shell. If you look at a tree branch in winter, you'll see buds, small swellings along the twigs. These buds are remarkable structures. Inside each one is a complete set of miniature leaves or flowers, already formed, just waiting for the right conditions to expand. These structures developed the previous growing season, often in mid to late summer. The tree created them, then wrapped them in protective scales and set them aside, essentially packaging next spring's growth and carrying it through the winter. The scales that cover buds are modified leaves, toughened and overlapping to create a waterproof, somewhat insulated chamber. Inside this chamber, the developing leaves or flowers are in a state of suspended animation, their growth paused but ready to resume when conditions improve. When spring arrives and the bud opens, what emerges was already there, just tightly folded and compressed. The bud doesn't create the leaves in spring. It simply allows them to unfold and expand. Spring can feel sudden because buds open quickly once conditions match. When a tree's requirements for breaking dormancy are finally met, the response can be remarkably rapid. One day, a tree stands bare-branched against the sky, and seemingly days later it's clothed in fresh green. The speed of this transformation is part of why spring can feel so dramatic, so full of sudden change. But from the tree's perspective, this isn't sudden at all. It's been prepared for months, with buds formed and ready. Once the environmental triggers align, the bud, scales separate. The compressed leaves inside begin to expand and cell division and cell expansion accelerate. Water rushes into the developing tissues, causing them to swell and unfold. Photosynthesis begins as soon as the leaves are exposed to light. Within a week or two, what was a bud becomes a fully expanded leaf or a flowering branch. The apparent suddenness is just the final, visible stage of a process that began the previous year and has been waiting patiently through the entire winter. Just one more small fact and then we drift. Forests often have layers: canopy, understory, shrub layer, and forest floor. When you walk into a mature forest and look around, you're seeing a vertical structure that's much more complex than it first appears. Ecologists often describe forests as having distinct layers, each with its own characteristic plants and conditions. At the top is the canopy, formed by the crowns of the tallest trees. These are the trees that have won the competition for light, reaching heights where they can spread their leaves above most of their neighbours. Below the canopy is the understory, a zone populated by smaller trees and young individuals of canopy species that haven't yet reached full height. Below that is the shrub layer, woody plants that remain relatively short at maturity. And at the bottom is the forest floor, where herbs, ferns, mosses and leaf litter dominate. These layers aren't always distinct. They blend into each other, and not every forest has all of them clearly defined. But the concept of layering helps us understand how forests organize themselves vertically as well as horizontally. The canopy catches most light, creating soft shade below. The upper canopy of a forest is where most of the action happens in terms of photosynthesis. These top leaves are exposed to full sunlight for much of the day, and they intercept the majority of the light energy reaching the forest. This creates wonderful conditions for the canopy trees themselves, but it also means that very little direct sunlight makes it through to the lower layers. The light that does penetrate is filtered and scattered by passage through the canopy. It's softer, greener, dappled. On the forest floor on a sunny day, you might see patches of bright light where gaps in the canopy allow sunlight through. But most areas are in shade. This shade is dynamic, shifting as the sun moves and as branches sway in the breeze. But overall, the effect of the canopy is to create a shaded environment below, cooler and dimmer than the sunny world above the trees. The understory is made of smaller trees and young saplings. In the dimmer light beneath the canopy, a different community of trees exists. Some of these are species that naturally stay small, adapted to life in shade. They grow slowly, but they can survive and even thrive with the limited light available. Others are young individuals of canopy species, waiting for their chance. These saplings may stay, small for years or even decades, growing very slowly in the low light. They're essentially biding their time, staying alive but not investing heavily in growth. They're waiting for an opportunity, for conditions to change in a way that will allow them to grow faster. This patience is a survival strategy. By staying alive in shade, even if they can't grow much, these saplings position themselves to respond quickly if more light becomes available. Shade-tolerant plants grow slowly, waiting for openings in the canopy. The ability to survive in shade is a valuable trait in a forest, but it comes with trade-offs. Shade-tolerant plants have adapted to make the most of low light levels. Their leaves may be larger or thinner to capture more of the limited light, or they may contain higher concentrations of chlorophyll. They tend to grow slowly because there simply isn't enough light energy to support rapid growth. But their slow growth is also efficient growth, investing resources carefully, avoiding waste. These plants can persist for long periods in the understory, waiting for an opening in the canopy above them. When that opening comes, whether from a branch falling or a tree dying, the shade-tolerant understory plant is positioned to respond, already established, already in place. It can begin growing faster, taking advantage of the increased light without having to establish itself from seed first. A gap can appear when an old tree falls, letting sunlight pour in. The death of a canopy tree is a significant event in a forest's life. When a large tree dies and falls, it creates what ecologists call a gap, an opening in the canopy where light can now reach the forest floor. The size and shape of the gap depend on the size of the fallen tree and what else it took down with it. Sometimes a falling tree's crown catches on neighbouring trees, creating a partial gap. Other times, particularly with very large trees or in storms where multiple trees fall, the gap can be substantial. Suddenly, a patch of forest floor that has been in shade for decades or centuries is bathed in sunlight. The light levels can increase 100-fold or more, the temperature rises, the soil can dry out more quickly. These changes are dramatic for the organisms living in that spot, but they're also an opportunity. Gaps can create mini-gardens of fast-growing plants. The sudden availability of light in a gap can trigger a rapid response from the plant community. Seeds that have been lying dormant in the soil, sometimes for years, can germinate. These are often seeds of fast-growing, light-demanding species, plants that specialize in colonizing disturbed areas. Seedlings of canopy trees that have been waiting in the understory can accelerate their growth dramatically, racing upward toward the light. Shrubs can expand. Even herbaceous plants can flourish temporarily in the bright conditions. The gap becomes a hotspot of growth and activity, a place where the normal slow pace of the forest accelerates into something more energetic. Over time, as trees grow up to fill the gap, the light levels will decrease again, and the plant community will change. But for a period of years or even decades, the gap represents a distinct patch within the forest, a place where different rules apply. Fallen logs are not waste, they're habitat and moisture storage. The tree that created the gap doesn't simply disappear. Its fallen trunk remains on the forest floor, and this large piece of dead wood becomes a resource in its own right. A fallen log can take decades or even centuries to fully decompose, depending on the tree species and the local climate. During all that time, the log serves multiple functions. It provides habitat for countless organisms. Insects bore into the wood. Fungi colonize it, breaking down the tough lignin and cellulose. Salamanders and small mammals shelter under it. As the log decays, it becomes softer and more absorbent, acting like a sponge that holds moisture. In dry periods, the inside of a rotting log can remain damp when the surrounding soil has dried out. This moisture makes the log a favourable spot for seeds to germinate and for roots to grow. The log also contains nutrients, all the carbon and minerals that the tree accumulated during its lifetime, and as it decays, these nutrients are slowly released. Many seedlings prefer the sheltered humidity near rotting wood. If you examine the forest floor in detail, you might notice that tree seedlings are often clustered around fallen logs. This isn't random. The microenvironment near a rotting log is different from the general forest floor. It's often more humid, protecting young seedlings from desiccation. The log can provide shelter from wind. The decaying wood itself can serve as a seedbed, with some seedlings actually germinating on top of the log and sending roots down into it as it softens. This association between young trees and old logs is common enough that fallen logs are sometimes called nurse logs, as if they're caring for the next generation of forest. It's a poetic image, but it's based on real ecological relationships. The death of one tree contributes directly to the establishment of new trees, a passing of resources from one generation to the next. Forest floors can be dominated by ferns, mosses and fungi. In many forests, particularly in temperate regions with adequate moisture, the forest floor is a green carpet of non-flowering plants. Ferns are common in many forest types, thriving in the shade and humidity. They reproduce through spores rather than seeds, and many species are well adapted to low light levels. Mosses are even more shade tolerant and can cover logs, rocks, and even the ground itself in thick, soft mats. Mosses have no true roots, absorbing water and nutrients directly through their leaves. They require moisture and are sensitive to drying out, so they're most abundant in forests where humidity stays high. Fungi, though not plants, are also highly visible on the forest floor, fruiting bodies of mushrooms emerging from the soil or from decaying wood. These visible mushrooms are just the reproductive structures of fungi. The main body of the fungus is a network of threads called hyphae, spreading through the soil or wood, invisible but enormously important to forest function. A healthy forest is often a patchwork of ages, textures and light. When ecologists study forests, they look for complexity and diversity, both in the species present and in the physical structure of the forest itself. A healthy forest typically isn't uniform, it's a mosaic of different patches in different stages of development. Here, a recent gap where young trees are racing upward. There, a mature area where the canopy is closed, and the understory is quiet. Somewhere else, a very old section where ancient trees dominate and dead wood is abundant. This patchwork pattern creates a diversity of habitats, which in turn supports a diversity of life. Different species need different conditions, and a forest that has many different patches can support many different species. The variation in light levels, moisture, temperature, and vegetation structure across a forest creates niches, specific sets of conditions that particular organisms can exploit. The patchwork nature of a forest is part of what makes it rich and resilient. Just one more small fact, and then we drift. Most forest life is out of sight, living in soil and leaf litter. When we walk through a forest, we naturally notice what we can see: the trees, the birds, perhaps a squirrel or deer. But the vast majority of living organisms in a forest are things we can't see without a microscope, or things that live hidden beneath the surface. The soil under our feet is teeming with life. Bacteria, fungi, protists, nematodes, arthropods, earthworms, and many other organisms make their homes in the top layers of soil and in the leaf litter above it. In a single handful of forest soil, there can be more individual organisms than there are humans on Earth. These tiny creatures perform essential functions, breaking down organic matter, cycling nutrients, helping plant roots function, aerating the soil. The forest above ground depends utterly on this hidden world below ground, yet we rarely see it or think about it. Soil is a mix of minerals, air spaces, water, and living organisms. When we think of soil, we might picture simple dirt, but soil is actually a complex and dynamic material. It begins with rock that has been broken down over time into mineral particles of various sizes: clay, silt, and sand. These mineral particles don't pack together perfectly. They leave spaces between them, pores where air and water can exist. In healthy soil, roughly half the volume is solid particles and half is pore space. The pore space is crucial because plant roots need both water and air. Too much water and the pores fill completely, suffocating. Roots. Too little water and plants can't get the moisture they need. Soil also contains organic matter, the partially decayed remains of plants and animals. This organic matter improves soil structure, helps it hold water and nutrients, and provides food for soil organisms. And finally, soil contains living things, from microscopic bacteria to visible creatures like earthworms. All these components interact to create a medium that can support plant life. Fungi help break down dead material into usable nutrients. Among the most important organisms in forest soil are fungi. Fungi are decomposers, specialists in breaking down complex organic molecules that many other organisms can't process. When a leaf falls or a tree dies, it's primarily fungi that begin the work of decomposition. Fungi produce enzymes that can break down cellulose and lignin, the tough structural materials that make up plant cell walls. They secrete these enzymes into the substrate, essentially digesting their food, externally, then absorbing the resulting nutrients. As fungi grow through dead wood or leaf litter, they fragment it, opening it up for other decomposers. They also absorb nutrients that were locked in the dead tissue and incorporate them into their own bodies. When the fungi die or are eaten by other organisms, those nutrients become available in different forms. Fungi are the recyclers of the forest, the organisms that ensure dead material doesn't simply accumulate, but instead is broken down and made available for new growth. Decomposition is slow recycling, not decay in a negative sense, just transformation. It can be easy to think of decomposition as destruction, as something negative. But from an ecological perspective, decomposition is creation. It's the transformation of dead material into nutrients and energy that living organisms can use. Without decomposition, all the nutrients taken up by plants would eventually be locked away in dead tissue unavailable for reuse. Growth would slow and eventually stop as available nutrients were exhausted. Decomposition prevents this. It completes the cycle, returning nutrients to the soil where they can be taken up by roots again. It's worth thinking of decomposition not as something rotting and ending, but as something being recycled and beginning again in a new form. The carbon atoms that were part of a leaf this year might be part of a root next year, then part of a mushroom, then part of another leaf. Nothing is truly lost. It's all just moving through the system, changing form but continuing to participate in the life of the forest. Many fungi form partnerships with tree roots called mycorrhizae. Beyond their role as decomposers, many fungi have evolved another strategy. partnership with living plants. These symbiotic relationships are called mycorrhizae, from Greek words meaning fungus root. In a mycorrhizal relationship, fungal hyphae colonize or closely associate with plant roots. The fungus and the plant exchange resources in a way that benefits both. The plant, through photosynthesis, produces sugars that it shares with the fungus. The fungus, spreading through the soil, gathers water and mineral nutrients and shares them with the plant. This partnership is ancient, probably dating back to when plants first colonized land hundreds of millions of years ago, and it's extremely common. Estimates suggest that more than 90% of plant species form mycorrhizal relationships. For trees in particular, mycorrhizae are often essential for healthy growth. In mycorrhizae, fungi trade minerals and water for sugars from the tree. The exchange in a mycorrhizal partnership is fairly straightforward in principle, though complex in detail. The tree, with its leaves in the sun, can manufacture sugars through photosynthesis. It produces more sugar than it needs for its own immediate use, and some of this excess is diverted to the fungus. The fungus, meanwhile, extends its hyphae through the soil far beyond where the tree's roots can reach. These hyphae are very fine, much thinner than root hairs, and they can penetrate tiny pores in the soil. This gives the fungus access to water and nutrients in soil volumes that roots can't access. The fungus absorbs these resources and transports them back to the root, where they're transferred to the tree. Both partners benefit. The tree gets enhanced access to nutrients and water, allowing it to grow better. The fungus gets a reliable source of sugars, allowing it to thrive. It's a mutually beneficial arrangement, a cooperation that has persisted for geological time. Fungal networks can spread widely, connecting many plants underground. One of the most fascinating aspects of mycorrhizal fungi is that a single fungal individual can associate with multiple plants simultaneously. The fungal network growing through the soil doesn't necessarily stop at the roots of one tree. It can extend to the roots of neighbouring trees, even trees of different species. This creates what's sometimes called a mycorrhizal network, or more popularly, a wood wide web, an interconnected system linking many plants through shared fungal partners. The implications of this network are still being researched, but it appears that the network can facilitate transfer of resources between plants. A tree in a sunny spot photosynthesizing actively might share some of its sugars through the network. These could end up supporting a tree in deep shade, or even a seedling trying to establish. In return, nutrients gathered by the fungus from one area of soil might end up in a tree some distance away. These networks can help seedlings by guiding water and nutrients through soil. For young seedlings, establishing in the challenging environment of the forest floor, connection to a mycorrhizal network can be crucial. A seedling with a tiny root system has limited ability to gather water and nutrients on its own, but if its roots are colonized by mycorrhizal fungi that are already part of an established network, the seedling gains immediate access to a much larger resource gathering system. The fungal hyphae can deliver water and nutrients to the seedling, helping it survive during its vulnerable early life. There's even evidence that established trees might, through the mycorrhizal network, transfer resources to their own seedlings, essentially parental care mediated by fungi. The network doesn't just move resources randomly. It appears that resources flow preferentially to plants that need them most, creating a kind of mutual support system within the forest community. Moss holds moisture like a sponge, stabilizing tiny microclimates. Mosses, though often overlooked, play important roles in forest ecosystems, particularly in moisture regulation. Moss tissue is structured in a way that allows it to absorb and hold large amounts of water relative to its dry weight. When it rains, moss swells with absorbed water. Then, over the following days, it slowly releases this water through evaporation. This creates a stabilizing effect on moisture levels in the immediate vicinity of the moss. While the surrounding air and soil might dry out quickly after rain, the area near a moss patch stays humid longer. For small organisms living in or on the moss, this stable humidity is valuable. For germinating seeds that land on moss, the reliable moisture can mean the difference between successful establishment and death from desiccation. In forests with abundant moss cover, particularly in cool, moist climates, the cumulative effect of all that moss is to make the forest floor more uniformly humid, with fewer dramatic swings between wet and dry. Forest soils can store water after rain, releasing it slowly over time. The soil in a forest does something similar to moss, but on a larger scale. The combination of mineral particles, organic matter, and pore spaces creates a structure that can absorb water when it's abundant and hold it for later use. When rain falls on a forest, some of it evaporates, some runs off, but much of it infiltrates into the soil. Once in the soil, water is held in the pore spaces by capillary forces. It doesn't all drain away immediately. Instead, it's stored, available to plant roots. Over the following days and weeks, roots extract this stored water, and some evaporates from the soil surface, but the process is gradual. The soil acts as a buffer, smoothing out the boom and bust cycle of rainfall. Even after a week or two without rain, a forest soil with good structure might still have water available to plants, while an exposed field with poorer soil structure might be completely dried out. This water storage capacity is one reason forests can maintain themselves through dry periods. Earthworms, insects, and microbes help mix soil and speed nutrient cycles. The activity of soil organisms doesn't just break down organic matter, it also physically rearranges the soil itself. Earthworms are famous for this. As they burrow, they consume soil and organic matter, digest what they can use, and excrete the rest as casts. In the process, they mix mineral soil with organic matter, improving soil structure. Their burrows create channels that allow air and water to penetrate deeper. Countless insects also live in soil, burrowing and tunneling, moving particles around. Roots grow and die, creating channels. Microbes produce sticky substances that help bind soil particles together into small aggregates. All this activity means that forest soil is not a static, stratified material. It's constantly being mixed, rearranged, processed. This mixing is important for maintaining soil quality, preventing compaction, and ensuring that nutrients are distributed and available where they're needed. The smell of a forest after rain comes partly from soil compounds released into the air. There's a particular smell that many people associate with forests, especially after rain. It's earthy, fresh, pleasant. This smell has multiple sources, but a significant component comes from soil. Certain soil bacteria, particularly actinomycetes, produce organic compounds called geosmins. When soil is disturbed or wetted, these compounds are released into the air. Geosmins have a very strong distinctive earthy odour that humans are quite sensitive to. We can detect them at very low concentrations. The scent of geosmin mixing with the scents of rain on leaf litter, wet wood and plant oils creates the complex smell we recognise as the scent of a forest after rain. It's a smell that signals moisture, signals growth, signals life. It's the smell of the forest systems activating, of nutrients cycling, of organisms responding to water's arrival. Dark, rich soil often signals high organic matter from long-term plant decay. When you dig into forest soil, particularly in older forests, you might notice that the upper layers are dark brown or almost black. This dark colour comes from organic matter in various stages of decay. Fresh plant material is relatively light in colour, but as it decomposes, the resulting compounds often become darker. The complex molecules created as decomposition proceeds include humic substances, which are dark brown to black. Soil high in these organic compounds looks dark and rich. This darkness is a sign of fertility, an indication that the soil has been accumulating and processing organic matter for a long time. It means there's a good supply of nutrients, good water holding capacity, good structure. Dark forest soil is the product of decades or centuries of leaves falling, decomposing, and being incorporated into the mineral soil, creating a medium that's ideal for plant growth. Old forests can build deep, stable soils over centuries. In forests that have existed for very long periods without major disturbance, soils can develop remarkable depth and structure. Each year's addition of leaf litter and dead roots adds to the organic content. Each year's activity by roots, fungi, and soil animals mixes and processes the material. Over decades, a layer of rich topsoil builds. Over centuries, this layer deepens. Old-growth forests sometimes have topsoil layers many feet deep, dark, loose, full of organic matter. This soil is a reservoir of nutrients, a storehouse of carbon, and a buffer against drought and other stresses. It's also fragile in a sense. If the forest is cleared, the soil, no longer protected by tree cover and no longer receiving annual inputs of leaf litter, can erode or degrade relatively quickly. But if the forest remains intact, the soil can persist for millennia. a stable foundation for the ecosystem above it. Even a single handful of forest soil can contain enormous microbial diversity. If we could somehow count and identify all the microorganisms in a small sample of forest soil, the numbers would be staggering. There are thousands of species of bacteria, fungi, protists, and other microscopic organisms in forest soil, and many of them are still unknown to science. These organisms perform countless functions. Some decompose specific types of organic matter. Some form symbiotic relationships with plants. Some are predators of other microbes. Some fix nitrogen from the air, making it available to plants. Some produce antibiotics or other chemicals that affect their neighbours. The microbial community in soil is as complex and diverse as the plant and animal community above ground, maybe more so, and this community is dynamic, changing in response to conditions, to the seasons, to the presence of different types of organic matter. Understanding soil microbiology is still a frontier in science, but we know enough to recognise that these invisible organisms are fundamental to forest function. Just one more small fact, and then we drift. Trees release water vapour through leaves in a process called transpiration. We've touched on this before, but it's worth exploring in more detail. Transpiration is the loss of water vapour from plants, primarily through the stomata in leaves. It's not accidental loss or waste. It's an essential part of how trees function. As water evaporates from the moist surfaces inside the leaf and exits through the stomata, it creates the pull that draws more water up from the roots. Transpiration is the engine that drives water movement through the tree. But it has other effects too. As water evaporates, it absorbs heat from the leaf, cooling it. On a hot day, a tree actively transpiring can keep its leaves at a temperature several degrees cooler than the surrounding air. This cooling effect doesn't just benefit the tree, it extends to the surrounding environment. Transpiration can cool the local air like a natural misting system. When water evaporates, it requires energy to change from liquid to vapour. This energy comes from heat in the immediate environment. As a tree transpires, releasing water vapour into the air, it's essentially pulling heat out of the surrounding air and converting it into the energy of evaporation. The net effect is cooling. A forest with millions of leaves all transpiring is releasing enormous amounts of water vapour and absorbing enormous amounts of heat in the process. This creates a local cooling effect. The air temperature inside a forest can be several degrees cooler than the temperature in an adjacent open area, even when both are under the same sunshine. This isn't just because of shade, it's also because of active cooling through transpiration. Forests create their own climate, and transpiration is a key part of how they do it. Forests can increase humidity under the canopy, making air feel softer. The water vapour released by transpiration doesn't disappear, it mixes with the air, increasing humidity. In a dense forest on a calm day, the humidity level can be significantly higher than in open areas nearby. This elevated humidity has several effects. It slows evaporation from soil, from leaf litter, from any moist surface, helping to maintain moisture levels. It can make the air feel softer, gentler, less harsh. High humidity can reduce the stress that plants and animals experience from drying. For humans spending time in a forest, the high humidity is often part of what makes the environment feel refreshing and restorative. It's not just that forests are quiet and shaded, they're also humid, and that humidity is a product of the trees themselves, of their transpiration, their release of water vapour into the air around them. Water vapour released by forests can help form clouds in the right conditions. The effects of forest transpiration can extend beyond the immediate forest environment. The water vapour released by trees rises into the atmosphere. In the right atmospheric conditions, this water vapour can contribute to cloud formation. Over large forested regions, the cumulative effect of transpiration from millions or billions of trees can release enough water vapour to influence regional weather patterns. Some research suggests that forests can help generate their own rainfall through this process. The trees transpire, releasing moisture into the air. This moisture rises, cools, and can eventually condense to form clouds and rain. The rain then falls back on the forest and the cycle continues. It's not a perfect closed loop. Forests aren't entirely self-sufficient in creating their rain, but they can influence the process, essentially recycling some of their water through the atmosphere. Some regions rely on large forests to support regular rainfall patterns. In certain parts of the world, particularly in tropical regions, forests play a crucial role in maintaining rainfall. The Amazon rainforest is a famous example. Trees in the Amazon absorb water through their roots and transpire it through their leaves. This water vapor rises into the atmosphere, forms clouds, and falls as rain, often within the same general region. The forest thus recycles water, pumping it from soil to air and back to soil in a continuous cycle. This process helps maintain the high rainfall that the forest needs to survive. If large areas of forest are removed, the transpiration decreases, humidity drops, cloud formation is reduced, and rainfall can decline. This can create a feedback loop where forest loss leads to reduced rainfall, which makes it harder for remaining forest to survive and easier for further forest to be lost. The connection between forests and rainfall is complex and varies by region, but in some places it's clear that forests don't just respond to climate, they help create it. Forests slow rain as it falls because leaves catch droplets and drip them gently down. When rain falls on a forest, it doesn't simply pour straight through to the ground. The leaves intercept much of the rainfall. Raindrops hit leaves and either evaporate, run along the leaf surface to the edge and drip off, or fall from leaf to leaf, working their way downward. This interception and redirection of rainfall slows its descent. Instead of rain hitting the ground at high speed, it arrives more gently, either as drips from leaves or as water that's run down branches and trunks. This gentler delivery of water to the ground reduces the impact force of rainfall. It's a softer, less erosive process than rain falling directly on bare soil. The canopy acts as a kind of umbrella, not keeping the ground dry, but moderating how water reaches it. This reduces erosion by preventing harsh impacts on bare soil. The impact of a raindrop on bare soil can be surprisingly forceful. The drop hits, splashes, and can dislodge soil particles, sending them flying. If this happens on sloped ground, the dislodged particles can start moving downhill, beginning the process of erosion. Over time, heavy rain on unprotected soil can cause significant soil loss. But in a forest, the canopy intercepts the rain and reduces its impact force. By the time water reaches the forest floor, it's been slowed and gentled. Additionally, the forest floor is usually covered with leaf litter, which provides further protection. Even if a raindrop does reach the ground with some force, it hits soft litter rather than bare soil. The combination of canopy interception and litter cover makes forest soils highly resistant to rain-caused erosion. The soil stays in place, rather than washing away. Roots stabilize slopes and can reduce landslide risk in some landscapes. Below ground, tree roots provide another form of erosion protection, particularly important on slopes. Roots penetrate the soil, creating a network of reinforcement. They act like rebar in concrete, holding the soil together. On steep slopes, the risk of landslides increases, especially during heavy rain when soil becomes saturated and heavy. But if the slope is forested, the root networks of the trees help hold the soil in place. Roots from multiple trees interweave, creating a reinforced mass that's much more resistant to sliding than unrooted soil would be. This effect is strongest in the upper layers of soil where root density is highest, but even deeper roots contribute. The loss of forest on steep slopes can dramatically increase landslide risk, as the stabilizing root networks decay and are not replaced. The presence of forest is often crucial for the stability of mountainous and hilly terrain. Forest streams often run clearer because vegetation filters sediment. The combination of reduced erosion and the filtering effect of vegetation means that streams and rivers flowing through forested watersheds often have very clear water. Sediment that might otherwise wash into the stream is held in place by roots and litter. Any sediment that does move tends to be trapped by vegetation before it reaches the stream. The roots and stems of plants along stream banks act as filters, catching particles. The result is water with low sediment load, clear enough to see through. This clarity isn't just aesthetic, it's important for aquatic life. Many stream organisms are sensitive to sediment. Excessive sediment can clog the gills of fish, smother the eggs of insects and amphibians, and reduce light penetration, affecting aquatic plants. Clear streams tend to be healthier streams, and the clarity is often a direct result of healthy forest in the surrounding watershed. Wetlands within forests act like sponges, storing and releasing water gradually. Some forests contain wetlands, areas where the soil is saturated with water for all or part of the year. These forested wetlands serve important hydrological functions. During periods of high rainfall or snowmelt, wetlands can absorb and store excess water. The saturated soil and standing water in a wetland represent storage, keeping that water from immediately flowing downstream. This storage reduces flood peaks downstream. Then, during drier periods, the stored water in wetlands slowly drains out, seeping into groundwater or trickling into streams. This slow release helps maintain stream flow during dry times. Wetlands thus smooth out the variations in water flow, reducing both floods and low flow periods. They're natural regulators of the water cycle, and when they're intact and functioning, they provide benefits far beyond their immediate location. Snow can linger longer in shady forests, melting slowly into spring. In regions with winter snow, forests influence the timing of snowmelt. Under the shade of evergreen canopy, snow is protected from direct sunlight. Temperatures are moderated. The snow that accumulates during winter can persist longer into spring than snow in open areas. This delayed melting has several effects. It extends the period during which water is being released from snowmelt, providing a longer, more gradual contribution to stream flow. In areas dependent on snowmelt for water supply, this gradual release can be more valuable than a rapid early melt. The prolonged presence of snow also affects soil moisture, keeping the ground cool and saturated for a longer period, which can benefit spring plant growth. The forest's influence on snow accumulation and melt is another example of how trees shape the physical environment around them. Forest edges can have different wind and temperature patterns than forest interiors. The boundary between a forest and open land is a special zone. At the edge, the trees are exposed to more wind, more direct sunlight, and more temperature variation than trees deeper in the forest. The edge often experiences stronger winds because there's no gradual reduction of wind speed, as there is when wind passes through the outer layers of the forest. The edge also heats up more during the day and cools more at night because it's partially exposed. These different conditions at the edge can select for different species. Some trees and plants thrive at edges, tolerating the harsher conditions and taking advantage of the increased light. The interior forest, by contrast, is more buffered, more stable, more protected. The existence of edges and interiors within a forest creates additional habitat diversity, allowing different species to find their preferred conditions. Just one more small fact, and then we drift. Forests are among the most biodiverse ecosystems on Earth. When ecologists study biodiversity, counting and cataloguing species, forests consistently rank among the richest ecosystems. Tropical rainforests are particularly notable, containing astounding numbers of species in relatively small areas, but even temperate forests harbour remarkable diversity. The structural complexity of forests, with their vertical layering and horizontal patchwork of conditions, creates many different niches. The long time that many forests have existed without major disturbance allows species to evolve and specialise. The moderate climate created by the forest itself allows species that might not survive in harsher conditions to persist. All these factors combine to make forests hotspots of biological diversity, places where life has proliferated into countless forms. Biodiversity includes not just animals, but plants, fungi, microbes, and insects. When we think about biodiversity, we might picture large animals, birds, mammals, perhaps reptiles and amphibians. And forests do support diverse animal communities. But the majority of species in a forest aren't animals at all. They're plants, yes, but even more so, they're fungi, insects, and microorganisms. A single forest might contain hundreds of plant species, thousands of insect species, countless fungal species, and more bacteria and other microbes than we could ever count. This microbial and invertebrate diversity is less visible than the diversity of birds or mammals, but it's equally important, maybe more so. These organisms drive nutrient cycling, decomposition, pollination, and countless other processes that keep the forest functioning. Biodiversity isn't just about what we can see easily. It's about the full spectrum of life, from the microscopic to the massive. Insects pollinate forest flowers and help decompose fallen material. Insects in forests play multiple crucial roles. Many forest plants depend on insects for pollination. Forest flowers might be visited by bees, flies, beetles, butterflies, and many other insect pollinators. Without these pollinators, many plants couldn't set seed and reproduce. At the same time, many insects are involved in decomposition. Beetles, flies, and ants break down fallen leaves, dead wood, and animal carcasses. They fragment large pieces into smaller ones, speeding the work of fungi and bacteria. Some insects, like termites and wood-boring beetle larvae, specialize in consuming dead wood. playing a key role in returning the nutrients locked in old trees back to the ecosystem. The diversity and abundance of insects in forests is often overlooked, but without them, forest ecosystems would function very differently and much less efficiently. Birds spread seeds by eating fruit and later dropping seeds elsewhere. Many forest trees and shrubs produce fleshy fruits. These fruits are designed to be eaten by animals, primarily birds and mammals. The fruit provides nutrition to the animal, and in return the animal disperses the plant's seeds. A bird eats a berry, digests the fruit pulp, and later excretes the seeds, often at a considerable distance from the parent plant. This dispersal service is valuable to the plant. It allows the plant's offspring to colonize new areas, to escape competition with the parent, and to reach favorable germination sites. Different bird species prefer different fruits and travel different distances, so plants that rely on bird dispersal have access to a variety of dispersal distances and directions. The partnership between fruiting plants and fruit-eating birds is one of many mutualistic relationships that structure forest communities. Some seeds are designed for wind travel with wings or fluffy fibers. Not all seeds rely on animals for dispersal. Many trees have evolved seeds or fruits that use wind. The seeds of maples and ashes have wings that allow them to spin as they fall, catching air and travelling some distance from the parent tree. Willows and cottonwoods produce seeds with fluffy fibres that act like parachutes, allowing the tiny seeds to drift on the slightest breeze, sometimes travelling miles. Pines and spruces have winged seeds that flutter away when their cones open. Each of these structures is an adaptation for wind dispersal, a way for the tree to spread its offspring without relying on animals. Wind dispersal is less precise than animal dispersal. The tree can't control where its seeds land, but it can be very effective for colonizing open areas or for simply ensuring that some seeds land in favorable spots by sheer numbers. Other seeds hitchhike on fur or feathers using tiny hooks. Another dispersal strategy is to stick to animals. Some seeds or fruits have small hooks, barbs, or sticky coatings that allow them to attach to the fur of mammals or the feathers of birds. The animal brushes against the plant, picks up the hitchhiking seeds, and carries them until they eventually fall off or are groomed away. This form of dispersal can be very effective because the animal often travels through the forest, potentially delivering seeds to a variety of locations. Plants using this strategy tend to produce seeds that are fairly robust, able to survive the journey stuck to an animal and the eventual fall or removal. The hooks are tiny but effective, and anyone who's walked through a forest and found burrs stuck to their clothing has experienced this dispersal method firsthand. Many forest animals are most active at dawn and dusk, when the world is quieter. The rhythm of the forest shifts over the course of a day. Midday, especially in summer, can be quite quiet. Many animals rest during the heat of the day, conserving energy and avoiding stress. But at dawn and dusk, the forest comes alive. These twilight periods, called crepuscular times, are when many animals are most active. Birds sing and forage. Deer emerge from resting spots to feed. Insects fly in the softer light. There are several reasons for this pattern. The cooler temperatures of morning and evening are more comfortable. The low angle of the sun creates particular light conditions that some animals prefer. Predators and prey have different advantages at different light levels, creating a complex dynamic. But the result is that dawn and dusk are the times when the forest feels most animated, most busy with life. Owls and bats help control insect populations in many forests. The nighttime forest has its own community of animals, including important predators. Owls are nocturnal hunters, using their exceptional hearing and silent flight to catch rodents, rabbits, and other small mammals. By preying on these animals, owls help regulate their populations, preventing overabundance that could lead to overgrazing of vegetation or bark. Bats, meanwhile, are often specialized insect predators. A single bat can consume thousands of insects in a night, including many species that are agricultural pests or disease vectors. In forests where bats are abundant, insect populations are kept in check, reducing damage to leaves and preventing insect outbreaks. Both owls and bats are adapted to navigate and hunt in darkness, filling ecological roles that diurnal predators can't fill. Woodpeckers create nesting holes that later shelter other animals. Woodpeckers are fascinating birds with a unique ecological role. They excavate holes in dead or living trees, using their strong beaks and specialized skulls to withstand the repeated impacts. They excavate these holes primarily for nesting, and sometimes for roosting. But once a woodpecker abandons a hole, it becomes valuable real estate for many other species. Birds that can't excavate their own cavities, such as chickadees, nuthatches, and bluebirds, use old woodpecker holes for nesting. Squirrels, bats, and even some insects use them for shelter. The holes created by woodpeckers thus benefit the wider forest community, providing habitat for cavity nesting species. In forests where woodpeckers are abundant, the availability of nesting cavities is higher, and populations of cavity nesting species tend to be more robust. Dead trees, called snags, are important homes for birds, insects, and fungi. When a tree dies but remains standing, it becomes what's called a snag. Snags might seem like they have no further role to play, but actually they're extremely valuable in forest ecosystems. The dead wood is habitat for wood-boring insects, which in turn attract woodpeckers. The bark peels and provides shelter for insects and spiders. Fungi colonize the wood, fruiting bodies emerging from cracks and holes, cavities, form, either excavated by woodpeckers or developing naturally as the wood decays, providing nesting sites. Snags are also perch sites for birds hunting from a vantage point. As the snag continues to decay, it becomes softer, easier for cavity nesting animals to modify. Eventually, the snag will fall, becoming a log on the forest floor where its role will change, but its value to the ecosystem will continue. The presence of snags is a sign of a healthy forest, with natural processes functioning. Different tree species support different communities of life. Not all trees are equal from a biodiversity perspective. Different tree species have different characteristics that affect what organisms can live on or in them. Some trees have bark that's particularly attractive to certain insects. Some produce flowers at times when few other resources are available, supporting pollinator populations. Some have dense canopies that create deep shade, favouring shade-loving understory plants. Some have leaves that decompose quickly, creating rich litter, while others have leaves that decompose slowly. A forest with high tree species diversity tends to support higher overall biodiversity, because each tree species brings with it a slightly different set of associated organisms. Mixing tree species creates a more complex, more varied forest, with more niches and more opportunities for different forms of life. A single old tree can be a small ecosystem of its own. An ancient tree, particularly one that's been standing for centuries, accumulates features over its lifetime. It might have broken branches, cavities, areas of dead wood mixed with living wood, loose bark and platforms where debris has collected. Its roots might have created mounds and hollows in the soil around it. Epiphytic plants like ferns or mosses might grow on its branches. All these features create microhabitats. Insects live in the cavities. Birds nest in the holes. Lichens encrust the bark. Small mammals might den at the base. Fungi fruit from dead wood. The tree becomes not just an organism but a structure that supports a community. Old trees are disproportionately valuable for biodiversity, supporting far more species than young trees of the same species. Their complex structure, accumulated over long time, provides opportunities that simple young trees can't match. Forests often feel peaceful, because life is spread out and layered, not crowded. There's a particular quality to the feeling of a forest, a sense of calm and space even when there's actually a great deal of life present. Part of this comes from the way life is distributed in a forest. Instead of being concentrated in a few spots, life is spread throughout the three-dimensional space. Some organisms are in the canopy, some in the understory, some on the ground, some below ground. Activity is distributed across time as well, with different species active at different hours. This spreading out means that at any given moment, in any given place, the forest doesn't feel crowded or chaotic. There's space between things. There's quiet mixed with sound. The complexity exists, but it's organised in a way that creates a sense of order and peace, rather than overwhelming busyness. Just one more small fact, and then we drift. Old-growth forests are shaped more by long time than by quick cycles. An old-growth forest is distinguished not just by the age of its trees, but by the fact that it has existed long enough for certain slow processes to have played out. These forests have escaped major disturbances for extended periods, allowing natural processes to proceed at their own pace. Large trees have grown, died, and fallen. Snags have stood for decades. Logs have decayed over centuries. Soil has deepened. The forest has reached a kind of mature state, though it's never truly static. Old-growth forests show the results of time. They're complex in structure, diverse in age classes of trees, rich in dead wood, and often home to species that depend on these specific features. They represent what forests become when given enough time and enough freedom from disturbance. They often have large trees, standing dead wood, and many layers of vegetation. The visual appearance of an old-growth forest is distinctive. The trees are often very large, with thick trunks and tall heights. This size comes from centuries of growth, from trees that germinated long ago and have been accumulating wood ever since. Mixed among the living giants are standing dead trees, snags in various stages of decay. Some are still structurally sound, others are leaning or hollow. The understory might be relatively open in some spots, shaded heavily by the canopy above, but in gaps where old trees have fallen, thick tangles of regenerating vegetation create dense patches. There are often multiple layers, from ground covers to shrubs to small trees to mature canopy. The overall impression is of complexity and verticality, of a space that's been organising itself for a very long time. Old trees can store carbon for centuries in their wood. One of the significant roles of forests in the global carbon cycle relates to carbon storage in wood. Trees, through photosynthesis, take carbon dioxide from the air and incorporate the carbon into their tissues. In a growing tree, carbon accumulates in wood, bark, roots, and leaves. A large old tree contains an enormous amount of carbon, accumulated over its lifetime. As long as the tree remains alive and standing, or even after it dies if the wood doesn't decay quickly, that carbon remains stored, locked up in solid form rather than floating free in the atmosphere as carbon dioxide. Old-growth forests, with their large trees and abundant dead wood that decays slowly, store very significant amounts of carbon. They're among the most carbon-dense ecosystems on Earth, holding more carbon per unit area than most other ecosystem types. Carbon in wood began as carbon dioxide in the air turned into structure by sunlight. It's worth tracing this path explicitly. A molecule of carbon dioxide drifts through the forest air. It happens to enter a leaf through a stoma. Inside the leaf, in a chloroplast, it encounters the light-driven reactions of photosynthesis. The carbon is extracted from the carbon dioxide and combined with other atoms to form glucose. The glucose might be used for energy, broken down to release the energy stored in its bonds, or it might be converted into cellulose or lignin, the structural molecules that make up wood. If it becomes part of wood, the carbon atom becomes part of the tree's solid structure. It might remain there for centuries, part of the trunk, helping to hold the tree upright. The tree has taken something gaseous and invisible and made it solid and structural. This transformation, from air to wood, is one of the fundamental processes that shapes our world. Forests are one of Earth's major carbon storage systems. At a global scale, forests contain enormous amounts of carbon. Estimates suggest that the world's forests hold hundreds of billions of tons of carbon in their trees, soils, and dead organic matter. This represents a significant portion of the carbon that cycles through the Earth's biosphere. Forests thus serve as a kind of bank, a place where carbon is deposited and held. As long as forests remain intact, this carbon stays stored. But if forests are cleared or burned, much of this carbon is released back into the atmosphere as carbon dioxide, contributing to climate change. Conversely, growing forests can remove carbon from the atmosphere, acting as a carbon sink. The role of forests in the carbon cycle is one of the reasons they're so important from a climate perspective. They're not just collections of trees, they're globally significant reservoirs and processors of carbon. Some trees can live for hundreds or even thousands of years. The longevity of trees is remarkable. Many common forest trees can live for several hundred years. Oaks, maples, and pines regularly reach ages of 2, 3, or even 400 years. But some species can live far longer. Giant sequoias and bristlecone pines in western North America can live for thousands of years. Some individual trees are among the oldest known living organisms on Earth, having germinated before the rise of ancient civilizations. These ancient trees have endured countless seasons, survived fires, droughts, storms, and pest outbreaks. They've witnessed changes in climate, in animal populations, in the forest around them. Their longevity is a product of slow growth, durable wood, and the ability to resist or recover from damage. They demonstrate that life doesn't have to be fast to be successful. Longevity often comes from slow growth, tough wood, and stable conditions. The oldest trees typically share certain characteristics. They grow slowly, adding small amounts of wood each year. This slow growth produces wood that's dense and durable, resistant to decay and pests. They often live in environments where competition is reduced by harsh conditions, high elevations, cold climates, nutrient-poor soils, places where other trees struggle, and the old individuals face less competition from faster-growing species. They're also often in locations that have escaped major disturbances like fire or logging. Longevity is not something a tree achieves alone. It's a product of the tree's biology interacting with environmental conditions and a good measure of luck. But when all these factors align, a tree can persist for millennia, a living link to the distant past. Old forests can be more resistant to drought in some cases because of deep soils and shade. There's some evidence that old forests, with their deep soils and closed canopies, can be more resilient to drought than younger forests. The deep soils that develop over centuries can store more water, providing a buffer during dry periods. The closed canopy creates shade and humidity that reduces evaporative stress. The extensive root systems of old trees can access water from deep in the soil profile. The presence of large amounts of organic matter in the soil improves water retention. All these factors can help an old forest weather drought better than a young forest, or a degraded forest with shallow, compacted soil. This doesn't mean old forests are invulnerable to drought, but it does suggest that the structural features that develop over long time can confer certain advantages in the face of environmental stress. Time in a forest can feel slower because change is subtle day to day. When you spend time in a forest, particularly if you return to the same forest repeatedly, you might notice that it seems timeless, unchanging. Of course, the forest is changing constantly. Leaves are growing and falling, trees are adding growth rings, seedlings are germinating, animals are being born and dying, fungi are spreading. But most of these changes are too slow, or too small to notice on a day-to-day or even year-to-year basis. A tree that was there last week is there this week, looking essentially the same. The forest creates an impression of stability and permanence because its changes happen at a pace that's slower than the pace of our lives. This can be part of why forests feel calming. They offer a different temporal scale, a reminder that not everything moves at the speed of human activity. A forest is never still. It's just changing at a gentle pace. Yet if we could watch a forest over decades or centuries, we'd see constant motion. Trees growing taller and wider, old trees dying and falling, gaps opening and closing, the composition of species shifting in response to climate or disturbance, soil deepening or eroding, animal populations rising and falling. The forest is dynamic, always in process. But the dynamics are slow, gentle, incremental. Change happens not in dramatic leaps but in small, steady accumulations. A millimetre of wood added each year becomes a massive trunk over centuries. A few seeds germinating each year maintains the population. This gentle pace of change is part of the forest character. It's a patient system, working on timescales that dwarf human lifetimes, but working nonetheless, always growing, always cycling, always becoming. Just one more small fact, and then we drift. Wooden furniture has stored sunlight, turned into solid structure over years. When you sit in a wooden chair or lean on a wooden table, you're touching something remarkable. That wood was once part of a living tree, and the substance of it, the carbon atoms that make up the cellulose and lignin, came from the air. They were carbon dioxide molecules that entered a leaf, were captured by photosynthesis, and were converted into solid structure using energy from sunlight. The wood you're touching is, quite literally, solidified light energy and air. Processed by a tree over years or decades, every piece of wood contains within it the history of the tree that made it, the seasons of growth, the sunlight captured, the water transported. Wood isn't just a material, it's a record, a transformation, a preservation of processes that happened long ago. Paper is also forest fibre, reshaped into thin sheets. Similarly, paper is wood that's been broken down and reformed. The wood is treated to separate the cellulose fibres, which are then suspended in water, spread into thin sheets, and dried. The result is a material that's radically different in form from wood, but still fundamentally made of the same substance. The carbon in paper came from the air, captured by trees. The structure of paper, when viewed under magnification, shows the individual cellulose fibres, remnants of the tree's cells. We use paper so casually, writing on it, wrapping things in it, discarding it, that it's easy to forget it's a product of forest ecology, of photosynthesis, of trees growing in sunlight, but each sheet is a transformed piece of forest carrying with it the carbon and structure that a tree created. Cotton, linen, and many plant fibers share the same carbon-building process as trees. This process of capturing carbon from air and building it into structure isn't unique to trees. Most plants do it. Cotton fibers, which come from the seed coats of cotton plants, are made of cellulose, just like wood. Linen, made from flax plant stems, is also cellulose. Many of the plant-based materials we use daily, from the paper we've already mentioned to the cotton in our clothes to the vegetables we eat, all represent captured atmospheric carbon, transformed through photosynthesis into solid, useful forms. It's all the same basic process, the same fundamental biochemistry. Plants take carbon dioxide and water, use sunlight as energy, and create sugars and other carbon-based molecules. We live surrounded by the products of this process, wearing them, sitting on them, eating them, often without thinking about where these materials came from or how they formed. The oxygen you breathe is continuously refreshed by photosynthesis around the planet. Every breath you take contains oxygen. Much of that oxygen was produced by photosynthesis, the same process we've been discussing. When a plant uses light energy to split water molecules during photosynthesis, one of the byproducts is oxygen gas, which is released into the air. This oxygen production is happening constantly, all around the world wherever plants are photosynthesizing. Forests, grasslands, agricultural fields, and especially the ocean's phytoplankton all contribute to maintaining the oxygen levels in the atmosphere. The oxygen you're breathing right now might have been released by a forest tree this morning, or by ocean algae last week, or by a crop plant last month. It's all part of the same global system, a continuous refreshment of the atmosphere's oxygen supply by the activity of photosynthetic organisms. Forest air can feel soothing, partly because of humidity and shade, not magic, just biology. There's often a sense that forests are special, almost mystical in their restorative effects. And while forests certainly can have positive effects on human well-being, much of this can be explained through straightforward biology and physics. The cool temperature from shade and transpiration is comfortable. The higher humidity is easier on skin and respiratory passages. The filtered light is gentler on the eyes. The muffled sound is less stimulating. The presence of plants releasing various organic compounds into the air creates distinctive scents, some of which humans find pleasant. These are all measurable physical phenomena. They don't require mysticism to explain, though that doesn't make them any less valuable. Understanding the mechanisms behind the forest's effects doesn't diminish them. If anything, it can deepen appreciation, revealing the complex interactions that create the experience of a forest. The calm you feel in forest can be linked to steady patterns, soft light, muffled sound, and predictable textures. There's a quality of steadiness in a forest environment. The light, though it shifts as the sun moves and as branches sway, has a consistent character. Dappled, green-tinted, softer than open sunlight. The sounds are muffled and often regular: wind in leaves, bird calls, the occasional creak of wood. There are few harsh, sudden stimuli. The visual environment, while complex, is made up of repeating elements: tree trunks, leaves, branches. There's a fractal quality to forest structure, patterns repeating at different scales. These steady, predictable patterns may be part of why many people find forests calming. The environment is complex enough to be interesting, engaging attention without demanding it. It's varied enough to avoid monotony, but patterned enough to be comprehensible. It provides sensory input without overwhelming the senses. Forests teach a quiet lesson. Growth doesn't have to be loud to be real. In a culture that often values rapid, visible progress, forests offer a different model. Trees grow slowly, imperceptibly on any given day, but steadily over time. The changes are real and substantial. A tree adds rings, gains height, develops complexity. But they happen quietly, without fanfare. There's no need for noise or drama. The work is done through consistent, incremental processes. Photosynthesis every sunny day, cell division in growing tips, transport of water and nutrients through xylem and phloem. These small, repeated actions accumulate into significant results. A seedling becomes a sapling, becomes a mature tree, becomes an ancient giant, all through this quiet, steady work. It's a reminder that meaningful growth and development don't require constant visible change or external validation. They simply require continuation, persistence, the patient accumulation of small efforts. Rest is part of the system. Trees have dormant seasons, and so do minds. The seasonal cycle of trees, particularly deciduous trees, includes dormancy. Growth stops, leaves fall. The tree rests through winter, conserving energy, waiting for favourable conditions to return. This rest is not failure or weakness. It's an essential part of the cycle, as important as the active growth of summer. The tree needs this downtime to survive, to prepare for the next growing season. In the same way, rest is essential for all living systems, including human minds. Periods of reduced activity, of quiet, of dormancy are not wasteful or unproductive. They're necessary. They allow for recovery, for consolidation, for preparation. The forest's seasonal rhythm is a model. There is a time for growth and activity, and there is a time for rest and stillness, and both are valuable, both are necessary. Even tonight somewhere, a forest is gently moving water, trading nutrients, and growing new cells. Right now, at this very moment, even as you read this, forests around the world are engaged in their quiet work. In daylight regions, leaves are photosynthesizing, roots are absorbing water and minerals, cells are dividing, wood is forming. In nighttime regions, respiration continues, water still moves through xylem, and roots still explore soil. The processes don't stop. Fungi are decomposing organic matter, releasing nutrients. Seeds are germinating. Animals are moving through the understory. Bacteria are fixing nitrogen. The forest is never truly at rest. It's a constant hum of biological activity, most of it invisible, most of it silent, but all of it part of the great cycles that sustain life. Somewhere, always, a forest is working, growing, changing, continuing. And you can let your thoughts do what forests do best. Slow down, soften, and simply continue. There's no pressure for your thoughts to be quick or loud or dramatic. They can drift like seeds on the wind, settling where they will. They can flow like water through xylem, moving, steadily without force. They can rest like trees in winter, quiet and patient. The forest doesn't rush, doesn't stress, doesn't demand. It simply continues, and in continuing, it thrives. Your mind can follow that same pattern. Release the need for speed or intensity. Allow your thoughts to slow to the pace of tree growth, to the gentle rhythm of seasons. Soften like filtered forest light, diffuse like humidity in shaded air. And simply continue, breathing in and breathing out, existing in this moment, part of the same world as those quiet forests, subject to the same gentle laws, held by the same patient systems. Let everything slow, let everything soften, let everything simply be and continue, like a forest in the long, slow work of being alive. Just one more small fact and then we drift, and drift, and drift. The next story is about to begin. Please relax and enjoy. The ocean is Earth's oldest habit. It has been here longer than mountains, longer than forests, longer than almost anything else you can see or touch on the surface of the planet. It covers more than 70% of the globe, and it holds about 97% of all the water on Earth. But the ocean is not just a giant container filled with liquid. It is motion and chemistry and temperature and time, all moving slowly together. It is a body that breathes without lungs, circulates without a heart, and shapes the world without ever hurrying. Tonight, we're not here to learn quickly. We're here to drift, to let facts settle gently, one after another, like sand sinking through clear water. There is no urgency, no test, no need to hold on tightly to every detail. The ocean itself does not rush, and neither will we. If your mind wanders, let it. If your eyes grow heavy, let them. The ocean will still be here, moving in its patient way, long after you have drifted into sleep. Just one more small fact, and then we drift. Picture a calm, dark surface. Soft waves, steady breathing. The ocean at night is not dramatic. It does not crash or roar unless a storm passes through, and storms are rare compared to the endless stretches of stillness. Most of the time, the ocean is simply there, vast, quiet, holding the planet the way a blanket holds warmth. It is always in motion, but the motion is gentle. Water moves in currents that flow like slow rivers. It rises and falls with the tides, pulled by the moon. It evaporates into the air and returns as rain. It is a cycle, a rhythm, a pattern that has been repeating for billions of years. Let us begin with the simplest question. What is the ocean made of? The answer is mostly water, of course, but not pure water. Seawater is a solution, a mixture of water and dissolved substances. The most abundant of these substances is salt. When we talk about salt in the ocean, we usually mean sodium chloride, the same kind of salt you might sprinkle on food, but there are other minerals dissolved in seawater as well. Magnesium, calcium, potassium, sulfate, and dozens of trace elements all float invisibly in every drop. The salt in the ocean comes from rocks and rivers, and it has been accumulating for a very long time. When rain falls on land, it is slightly acidic, and as it flows over rocks and soil, it slowly dissolves minerals. These minerals are carried by rivers into the sea. Once in the ocean, the water evaporates, but the salt does not. It stays behind, and over millions and millions of years, the ocean has become saltier. Not dramatically salty. Seawater is about 3.5% salt by weight, but enough to change the way it behaves. Saltwater freezes at a lower temperature than fresh water. Pure water freezes at 0 degrees Celsius, but seawater does not freeze until it reaches about -2 degrees Celsius. This is one reason why the ocean near the poles can remain liquid even in the coldest months, though. Sea ice does form when temperatures drop low enough. The ice that forms is less salty than the water it came from, because as water freezes, it tends to exclude the salt. This means that the water left behind becomes slightly saltier, slightly denser, and slightly more likely to sink. The ocean feels alive with chemistry even when it looks perfectly still. Oxygen dissolves in seawater, especially at the surface where waves mix air and water together. This dissolved oxygen is what allows fish and other marine creatures to breathe. Carbon dioxide also dissolves in seawater, and the ocean holds an enormous amount of it, far more than the atmosphere. This makes the ocean an important part of Earth's carbon cycle, absorbing carbon dioxide from the air and storing it in various forms for long periods of time. Temperature shapes the ocean in quiet, powerful ways. Sunlight warms the surface, but it does not penetrate very deep. The top layer of the ocean, warmed by the sun, can be quite comfortable, warm enough to swim in tropical regions. But below that warm surface layer, the temperature drops. There is often a boundary called the thermocline, a zone where temperature decreases rapidly with depth. Below the thermocline, the ocean is cold. Not freezing, but cold and steady, hovering just a few degrees above freezing no matter where you are on the planet. The deep ocean does not experience seasons. It does not warm in summer or cool in winter. It simply stays cold, patient, and dark. This layering of temperature is one reason the ocean is not a uniform soup. It is stratified, divided into zones based on temperature, salinity, and density. Warm water is less dense than cold water, so it tends to float on top. Salty water is denser than fresh water, so it tends to sink. These differences in density create structure, and structure influences how water moves. Just one more small fact, and then we drift. The ocean is mostly quiet mass. It does, not thrash or sprint. It holds more than 300 million cubic miles of water, and that water has weight and inertia. It takes time and energy to move it, and once it is moving, it takes time and energy to stop it. This is part of why the ocean is so steady, so calm in its core nature. Yes, there are waves on the surface, and yes, there are currents flowing through it, but these are small expressions of motion in an overwhelmingly large body. The ocean is not in a hurry. It measures time in centuries, in millennia, and ages. Now let us turn to motion. The ocean moves without hurry, and yet it is always moving. One of the most familiar motions is the tide. Twice a day in most places the ocean rises and falls. This is not because the ocean is breathing or because water is being added and removed. It is because the moon, and to a lesser extent the sun, are pulling on the water. Gravity is the key. The moon's gravity pulls on the Earth, and because water is more fluid than rock, it responds more easily to that pull. The water on the side of the Earth facing the moon is pulled slightly toward the moon, creating a bulge. At the same time, on the opposite side of the Earth there is another bulge. This happens because the Earth itself is also being pulled toward the moon. but the water on the far side is farther away from the moon and feels slightly less pull, so it lags behind, creating a second bulge. As the Earth rotates, different parts of the coastline move through these bulges, and we experience this as high tide and low tide. The sun also affects the tides, though its effect is smaller because it is much farther away. When the sun, moon, and Earth line up, during a new moon or a full moon, the sun's pull and the moon's pull work together, creating higher high tides and lower low tides. These are called spring tides, though they have nothing to do with the season. When the sun and moon are at right angles to each other, their pulls partially cancel out, creating smaller tidal ranges called neap tides. Tides are a slow-breathing pattern. They are predictable, rhythmic, and ancient. Long before humans built clocks, the tides kept time. Sailors learned to read them, to wait for high tide to enter a harbour, or to leave on an outgoing tide. Even today, the tides shape coastal life, when boats can launch, when certain animals feed, when sand is exposed or covered. But tides are not the only way the ocean moves. There are also currents, long invisible rivers inside the sea. Some currents flow near the surface, driven by wind. Others flow deep below, driven by differences in temperature and salinity. Together, these currents form a global circulation system that connects all the ocean basins. Surface currents are shaped by the wind, but also by the rotation of the Earth. When wind blows across the ocean, it drags the surface water along with it. But the water does not move in exactly the same direction as the wind. Because the Earth is rotating, the moving water is deflected to the right in the northern hemisphere and to the left in the southern hemisphere. This effect is called the Coriolis effect, and it helps create the great loops of surface currents that circle the ocean basins. In the North Atlantic, for example, there is a current system called the North Atlantic Gyre. Warm water flows from the equator up along the coast of North America as the Gulf Stream, then continues northeast across the Atlantic toward Europe. As it cools, it turns southward, flowing down along the coast of Africa before curving back west toward the equator. This loop is thousands of miles across and flows continuously, moving warm water poleward and cool water equatorward. The Gulf Stream itself is a remarkable current. It is narrow, only about 60 miles wide in places, but deep and fast, carrying more water than all the rivers on Earth combined. It flows at several miles per hour, which may not sound fast, but for an ocean current it is brisk. The warmth it carries northward moderates the climate of Western Europe, making places like Ireland and the United Kingdom much milder than other regions at the same latitude. Surface currents like the Gulf Stream are important for moving heat around the planet. The sun warms the equator more than the poles, and without some way to redistribute that heat, the tropics would grow hotter and the poles would grow colder. Ocean currents, along with atmospheric winds, help balance the temperature, carrying warmth from the equator toward the poles and returning cooler water back toward the tropics. But not all currents flow at the surface. Some of the most important currents flow deep in the ocean, far below where wind or sunlight can reach. These deep currents are driven by differences in density, which in turn are driven by differences in temperature and salinity. This process is sometimes called thermohaline circulation, from the Greek words for heat and salt. Here is how it works. In the polar regions, especially near Greenland and Antarctica, the surface water becomes very cold. Cold water is denser than warm water. At the same time, when sea ice forms, it leaves behind saltier water, which is also denser. This cold, salty water sinks. It sinks all the way to the ocean floor and then it begins to flow. It flows along the bottom of the ocean, creeping slowly across the seafloor, moving from the poles toward the equator. This deep water can take hundreds or even thousands of years to complete its journey. It flows through the deep basins of the Atlantic, then loops around the southern tip of Africa and enters the Indian and Pacific Oceans. Eventually it rises back to the surface in certain regions, warmed by the sun and mixed back into the surface circulation. The entire loop of sinking, flowing, rising and returning is called the global ocean conveyor belt, and it is one of the slowest, steadiest circulations on Earth. Just one more small fact, and then we drift. Understanding currents helps us see the ocean not as a static pool, but as a body in constant quiet motion. Warm water tends to ride higher, cold, salty water tends to sink, and the planet's rotation helps steer everything into broad looping paths. These currents shape climate, influence weather, and create invisible highways that marine life has learned to navigate. There are also smaller temporary currents caused by local conditions. Wind can pile water up against a coast, and when the wind stops, the water flows back out in a current. Tidal currents flow in and out of bays and estuaries as the tide rises and falls. Near the equator, there are currents that oscillate back and forth across the Pacific in patterns that influence weather worldwide. One of these patterns is called El Niño, a periodic warming of the central and eastern Pacific that can shift rainfall, droughts, and storms across entire continents. Sailors once relied on ocean currents like maps made of water, before engines, before satellites, before GPS, knowing the currents meant the difference between a quick voyage and a slow, dangerous one. Ships travelling from Europe to the Americas learned to catch the westward flowing currents near the equator, then ride the Gulf Stream back home. These routes were traced and retraced, generation after generation, as reliable as roads. Even today, currents matter. They influence shipping routes, fishing grounds, and the spread of nutrients. They carry warmth and cold, oxygen and carbon, salt and fresh water. They connect distant parts of the ocean, making it not a collection of separate seas, but a single, interconnected body of water. Why do some coasts feel cooler than others, even at the same latitude? Often, it is because of currents. A cold current flowing along a coastline will keep the air above it cool, and when that cool air drifts over land, it brings fog and mild temperatures. The coast of California, for example, is cooled by the California Current, which flows southward from the North Pacific. In summer, when the land heats up, the cool ocean air creates fog that rolls in over coastal cities. The same principle applies in other regions. Where cold currents flow, coasts tend to be cooler and often foggier. The ocean's surface is not uniform, it has texture. There are regions where currents converge, pushing floating debris and plankton into long lines. There are regions where water upwells from below, bringing nutrients to the surface and creating rich feeding grounds for fish and seabirds. There are gyres where water circulates slowly, accumulating whatever floats and does not sink. The ocean is not just deep and wide, it is patterned, layered, and full of subtle structure. Just one more small fact, and then we drift. Now let us drift downward, peacefully, not with fear, but with curiosity. The deep ocean is not a dangerous void. It is simply different. It is a place where pressure increases, where darkness is complete, and where the rules of life take on new forms. Pressure in the ocean increases with depth. For every 10 meters you descend, the pressure increases by about 1 atmosphere. The same pressure you feel at sea level. At 100 meters deep, the pressure is 10 times greater than at the surface. At 1,000 meters, it is 100 times greater. At the deepest point in the ocean, the Mariana Trench, the pressure is more than 1,000 times what we experience on land. But pressure is not crushing in the way we might imagine. It is simply force evenly distributed. Creatures that live in the deep ocean have bodies adapted to that pressure. They do not feel crushed because the pressure inside their bodies matches the pressure outside. There are no air pockets to collapse, no rigid structures to buckle. The deep ocean is not hostile to life. It is simply a different kind of home. Darkness is another defining feature of the deep. Sunlight does not penetrate far into the ocean. The surface is bright, lit by the sun, and the top layer, perhaps the first 10 or 20 meters, is warm and well lit. Below that, light fades. By about 200 meters, there is very little light left. By 1,000 meters, it is completely dark, a darkness so total that no human eye could detect even a glimmer. This means that the deep ocean is a world without seasons, without day or night in the way we know them. There is no sunrise to wake to, no sunset to mark the end of the day. Time passes, but it is measured differently, by currents, by the slow drift of food from above, by the patient rhythms of life adapted to the dark. The seafloor is not flat. If you could drain the ocean and walk across the bottom, you would find mountain ranges taller than the Himalayas, valleys deeper than the Grand Canyon, volcanoes, ridges, plains, and plateaus. There are underwater mountain ranges called mid-ocean ridges, where tectonic plates pull apart and new seafloor is formed. There are trenches where one plate dives beneath another, descending into the Earth's mantle. There are seamounts, underwater mountains that rise from the seafloor but do not quite reach the surface. Some of these seamounts are extinct volcanoes worn smooth by the slow passage of time. The mid-ocean ridges are some of the longest mountain ranges on Earth, stretching for tens of thousands of miles through the Atlantic, Pacific and Indian Oceans. They are not sharp, jagged peaks, but broad, gentle rises with a rift valley running down the centre. At the rift, hot magma wells up from below, cools, and solidifies into new rock. This process, called seafloor spreading, pushes the older rock outward, slowly widening the ocean basin. It is one of the ways the Earth renews itself, creating new crust in some places while destroying old crust in others. Trenches are the deepest parts of the ocean. The Mariana Trench in the western Pacific reaches a depth of nearly 11,000 metres, almost 7 miles. If you placed Mount Everest at the bottom of the trench, its peak would still be more than a mile underwater. Trenches are formed where tectonic plates collide, and one plate is forced beneath the other in a process called subduction. They are narrow, steep-sided and cold, and they mark the zones where the ocean floor is being pulled back into the earth. Between the ridges and the trenches lie the abyssal plains, vast flat regions of seafloor covered in fine sediment. These plains are some of the flattest places on Earth, stretching for hundreds or thousands of miles with barely any change in elevation. The sediment is made of tiny particles, dust blown from land, the remains of microscopic sea creatures, volcanic ash, and bits of rock carried by currents. It settles slowly, accumulating over millions of years, layer upon layer, like snow drifting onto a quiet field. Sound travels differently in water than in air. In air, sound moves at about 340 meters per second. In water, it moves more than 4 times faster, about 1,500 meters per second. This means that sound can travel long distances underwater. Whales use this to their advantage, sending low-frequency calls across entire ocean basins to communicate with one another. A whale's song, sung off the coast of one continent, can be heard thousands of miles away by another whale. The deep ocean is cold and stable. While the surface may warm and cool with the seasons, the deep ocean remains at a nearly constant temperature, just a few degrees above freezing. This stability makes it a refuge for creatures that prefer consistency. There are no sudden temperature swings, no storms to disrupt the quiet. Life in the deep is slow, patient, and finely tuned to the conditions. One of the most remarkable discoveries in deep-sea exploration was the finding of hydrothermal vents, places where hot, mineral-rich water pours out of cracks in the seafloor. These vents form along the mid-ocean ridges where seawater seeps into the crust, is heated by magma below, and then shoots back out through chimney-like structures. The water can be hundreds of degrees Celsius, hot enough to boil on the surface, but under the immense pressure of the deep ocean, it remains liquid. Around these vents, entire ecosystems have formed, relying not on sunlight but on the chemical energy in the vent fluids. Bacteria use a process called chemosynthesis to convert the chemicals, mostly hydrogen sulfide, into energy. These bacteria form the base of the food web, supporting communities of tube worms, clams, shrimp and crabs. It was a revelation when these ecosystems were first discovered in the late 1970s because it showed that life does not always need sunlight. It can thrive in total darkness, in extreme heat and pressure, sustained by chemistry alone. Just one more small fact, and then we drift. The deep ocean is not empty. It is quiet, slow, and spacious, but it is full of life. There are fish with enormous eyes adapted to catch the faintest glimmers of light. There are fish with no eyes at all, navigating by touch and vibration. There are jellyfish that pulse gently through the dark, translucent and fragile. There are squid that hunt in the twilight zone, the region between the sunlit surface and the pitch-black deep. There are creatures with bodies so soft they seem almost liquid, perfectly suited to the pressure and the stillness. Let us rise now, gently, back toward the light, and talk about ocean life as soft wonder. Life in the ocean comes in every imaginable form, from the smallest drifting bacteria to the largest animals ever to exist, and much of it is quiet, beautiful, and perfectly adapted to the world it inhabits. Plankton are the drifters. The word comes from the Greek word for wanderer, and it describes organisms that float or drift with the currents, unable to swim strongly against them. Plankton include both plants and animals. Phytoplankton are microscopic photosynthetic organisms mostly single-celled algae that float near the surface where sunlight can reach them. They are so small that a single drop of seawater can contain thousands of them, and they are so abundant that they produce more than half of the oxygen in Earth's atmosphere. Every other breath you take you owe to phytoplankton. Zooplankton are the animal counterpart. They include tiny crustaceans, larval forms of fish and invertebrates, and other small creatures that drift with the currents. Some zooplankton eat phytoplankton, others are predators, hunting other zooplankton. Together, phytoplankton and zooplankton form the base of the ocean's food web. Almost everything else in the ocean depends on them directly or indirectly. The great whales, the fastest fish, the sprawling kelp forests, all of it traces back to these tiny drifting organisms. One of the most enchanting features of ocean life is bioluminescence, the ability to produce light. In the deep ocean, where sunlight never reaches, many organisms have evolved the ability to glow. They produce light through chemical reactions, usually involving a molecule called luciferin and an enzyme called luciferase. When these substances combine in the presence of oxygen, they emit a soft, cold light, blue or green usually, because those colours travel farthest in water. Bioluminescence is used for many purposes. Some creatures use it to attract prey, dangling a glowing lure in the darkness to tempt smaller animals close. Others use it to communicate, flashing patterns to signal mates or warn rivals. Some use it for camouflage, producing light on their undersides to match the faint glow of sunlight from above, making themselves invisible to predators looking up from below. And some use it defensively, releasing clouds of glowing fluid to startle or confuse attackers. The effect is like underwater starlight. Imagine sinking into the dark ocean, and as your eyes adjust, you begin to see soft pulses of blue-green light, jellyfish drifting by, their bodies glowing faintly, tiny shrimp darting away in bursts of brightness, larger shapes outlined in luminous patterns. It is a quiet, peaceful display, not dramatic but steady, a reminder that even in the darkest places there is light. Coral reefs are slow-built cities. They are made of the skeletons of tiny animals called coral polyps. Each polyp is small, often just a few millimeters across, and it builds a cup-shaped skeleton of calcium carbonate around itself. When the polyp dies, the skeleton remains, and new polyps build on top of it. Over centuries and millennia, these skeletons accumulate into massive structures, reefs that can stretch for hundreds of miles. Coral reefs are among the most diverse ecosystems on Earth. Though they cover less than 1% of the ocean floor, they support about a quarter of all marine species: fish, crustaceans, mollusks, sponges, sea stars, urchins, and countless other organisms live among the coral, finding shelter, food, and breeding grounds. The structure of the reef creates endless nooks and crannies, each one a potential home. The corals themselves are not just rock. The living polyps have a symbiotic relationship with microscopic algae called zooxanthellae, which live inside the coral tissue. The algae photosynthesize, producing food for the coral. In return, the coral provides a safe place to live and access to sunlight. This partnership is delicate. If the water becomes too warm or too polluted, the coral can expel the algae in a process called bleaching. Without the algae, the coral turns white and, if conditions do not improve, may die. Reefs grow slowly. A coral colony might grow only a centimetre or two per year. Large ancient reefs may be thousands of years old, built layer upon patient layer. They are monuments to slow, steady growth, to the accumulation of small efforts over long time. Kelp forests are another kind of underwater forest, found in cooler coastal waters. Kelp is a type of large brown algae, and the fastest growing forms can grow more than 0.5 metre per day in ideal conditions. Kelp anchors itself to the seafloor with a root-like structure called a holdfast, and from there it sends up long, flexible stipes that rise toward the surface. At the top, broad blades spread out to catch sunlight, and gas-filled bladders help keep the kelp upright. A kelp forest sways with the current, bending and flowing like tall grass in the wind. Light filters down through the blades, creating dappled patterns on the seafloor. Fish weave between the stipes. Sea otters wrap themselves in kelp fronds to keep from drifting away while they sleep. The kelp softens the force of waves, creating calmer water behind it and protecting the shore from erosion. Kelp is food for many animals. Sea urchins graze on it, and if their populations grow too large, they can clear. entire kelp forests turning them into barren rock. But where predators like sea otters keep the urchins in check, the kelp thrives, creating a rich, productive ecosystem. Migration is one of the ocean's quiet wonders. Many marine animals travel vast distances, following seasonal patterns, food sources, or the pull of instinct. Grey whales migrate from the cold waters of the Arctic to the warm lagoons of Baja California to give birth, a journey of more than 10,000 miles round trip. They travel slowly, staying close to the coast, and they do this every year. Sea turtles navigate across entire ocean basins, sometimes travelling thousands of miles, to return to the very beach where they were born. How they find their way is still not entirely understood. They may use the Earth's magnetic field, the angle of the sun, the taste of the water, or some combination of cues. Whatever the method, it works. Year after year, turtles return to the same beaches, dig nests in the sand, lay there, eggs, and then swim back out to sea. Fish migrate too. Salmon are born in freshwater streams, swim downstream to the ocean, spend years feeding and growing in the open sea, and then return to their home stream to spawn. They navigate upstream, against the current, sometimes leaping over waterfalls and obstacles, driven by an urge that has shaped their species for millennia. Even tiny plankton migrate, though their journey is vertical rather than horizontal. Many zooplankton spend the day in the deep, dark water where they are safer from predators. At night, they swim upward toward the surface to feed on phytoplankton. This daily journey, repeated by countless billions of individuals, is one of the largest movements of biomass on the planet. Schools of fish move like living brushstrokes. Thousands or even millions of individuals swim together, turning in unison, creating shapes that flow and shift. Each fish follows simple rules. Stay close to your neighbours, match their speed, avoid collisions, and from these simple rules, complex coordinated behaviour emerges. A school can confuse predators, making it hard to single out one individual. It can also make finding food easier, as many eyes are better than one. Even the strangest creatures of the deep are calm solutions to deep water living. The anglerfish, with its glowing lure and enormous mouth, is not a monster, but a patient hunter, waiting in the dark for prey to come within reach. The giant squid, with the eyes the size of dinner plates, is not a terror, but a deep-sea predator adapted to sea in near-total darkness. The gulper eel, with its huge hinged jaw, is designed to swallow prey larger than itself, a useful trait in a place where meals are rare and unpredictable. Life in the ocean is efficient, quiet, and perfectly adapted. There is no wasted motion, no drama, just the slow unfolding of survival and reproduction over millions of years. Just one more small fact, and then we drift. Now let us zoom out, still soothing, and see the ocean as part of the whole planet. The ocean is not separate from the land, the air, or the sky. It is connected to everything, shaping weather and climate, feeding the water cycle, and influencing the very composition of the atmosphere. The ocean stores and moves heat. It absorbs sunlight, especially in the tropics, and because water has a high heat capacity, it can hold that warmth for a long time. Currents carry the warm water poleward, releasing heat into the atmosphere as they go. This helps moderate the planet's climate, keeping the tropics from overheating and the poles from becoming even colder. The ocean also stores heat in deeper layers. When the surface warms, some of that heat is mixed downward by waves and currents. The ocean holds far more heat than the atmosphere, about 1,000 times more in fact. This makes it a buffer, absorbing excess heat and releasing it slowly over time. Without the ocean, the Earth's climate would be much more volatile, swinging between extremes. Evaporation from the sea is the beginning of the water cycle. The sun warms the ocean surface, and water molecules escape into the air as vapour. This vapour rises, cools, and condenses into clouds. The clouds drift over land, and the water falls as rain or snow. The rain feeds rivers, lakes, and groundwater, which eventually flow back to the sea, completing the cycle. Most of the rain that falls on land comes from water that evaporated from the ocean. In this way, the ocean is the source of almost all fresh water. It is the planet's great reservoir, constantly giving up water to the sky and receiving it back over and over in a rhythm that has been going on for as long as there has been liquid water on Earth. Sea ice and salty water affect circulation in subtle but important ways. When sea ice forms in polar regions, the water left behind becomes saltier and denser. This dense water sinks and drives deep ocean currents, which in turn help distribute heat and nutrients around the globe. If the formation of sea ice slows or stops, the circulation can weaken, which can have far-reaching effects on climate and ocean ecosystems. Coastal air often carries the ocean's fingerprint. If you live near the coast, you may have noticed that the air feels different, often cooler in summer, milder in winter, and more humid year-round. This is because the ocean moderates temperature. Water heats and cools more slowly than land, so the ocean acts as a thermal buffer, keeping coastal regions from experiencing the extremes that inland areas do. The smell of the sea is real, and it comes from chemicals produced by marine organisms. One of these chemicals is dimethyl sulfide, produced by phytoplankton. When it evaporates into the air, it gives the ocean its characteristic scent. This scent is not just pleasant, it also plays a role in cloud formation. Dimethyl sulfide can act as a nucleus for water vapour to condense around, helping to form clouds over the ocean. The ocean is distant but not separate from you. The water in your body, about 60% of your mass, echoes the planet's water cycle. You drink water that once evaporated from the sea, fell as rain, flowed through rivers, and was purified for your use. You breathe out water vapour with every breath. You sweat and the water evaporates, returning to the air. Salt helps your nerves and muscles work. Your cells are bathed in a salty fluid, not unlike seawater in its composition, though much less concentrated. This is a reminder that life began in the ocean, billions of years ago, and that even now, landlocked and far from the coast, we carry the ocean's chemistry inside us. The ocean's chemistry is vast and complex. It absorbs carbon dioxide from the air, which reacts with seawater to form carbonic acid. This makes the ocean slightly acidic, though still on the basic side of the pH scale. The ocean can absorb enormous amounts of carbon dioxide, which has been important in regulating Earth's climate over geological time. However, the rate at which carbon dioxide is currently being added to the atmosphere is faster than the ocean can easily absorb, and this is causing changes in ocean chemistry that scientists are still studying. The ocean influences weather in direct and indirect ways. Hurricanes and typhoons form over warm ocean water, drawing energy from the heat stored in the sea. The evaporation of ocean water adds moisture to the atmosphere, which can fuel storms. Ocean currents can steer weather patterns, guiding storms along certain paths or blocking them from others. El Niño, mentioned earlier, is a pattern of warming in the central and eastern Pacific that occurs every few years. When it happens, it can shift rainfall patterns across the globe. Some regions that are normally dry receive heavy rains, others that are normally wet experience drought. Fisheries can be affected, as the warm water disrupts the usual upwelling of nutrients. The effects of El Niño can last for months, demonstrating how changes in the ocean can ripple through the entire climate system. Even the quiet sea is never truly still. There is always some motion, currents flowing, tides rising and falling, waves travelling across the surface. Energy is always passing through the water, even when it looks calm. This constant, gentle motion is part of what makes the ocean feel alive. Just one more small fact, and then we drift. Now we come to the slowest perspective, the deepest time. The ocean has not always looked the way it does today. Over hundreds of millions of years, continents have drifted, collided, and split apart. Shorelines have wandered, ocean basins have opened and closed, and through it all the ocean has kept moving. Patient, steady, unbothered. 300 million years ago, the continents were joined together in a supercontinent called Pangaea. The ocean that surrounded it was called Panthalassa, and it was vast, far larger than any ocean today. Over time, Pangaea broke apart and the pieces drifted slowly across the globe. As the continents moved, new ocean basins opened between them. The Atlantic Ocean, for example, is relatively young. It began to form about 200 million years ago, as North and South America separated from Europe and Africa. The ocean floor is constantly being renewed. New crust forms at the mid-ocean ridges, and old crust is pulled back into the earth at the trenches. This means that the oldest seafloor is only about 200 million years old, which is young compared to the age of the Earth. The ocean water itself is much older, billions of years, but the floor beneath it is constantly recycled. Currents have rearranged over time as continents have shifted. The opening or closing of a seaway can redirect entire current systems. For example, the formation of the Isthmus of Panama about 3 million years ago closed the connection between the Atlantic and Pacific Oceans. This forced currents to reroute, which may have strengthened the Gulf Stream and influenced the climate of the Northern Hemisphere. Sea level has risen and fallen many times. During ice ages, when vast amounts of water were locked up in glaciers, sea level was much lower than it is today, sometimes more than 100 meters lower. Shorelines extended far beyond where they are now. Land bridges appeared, connecting continents and allowing animals to migrate. When the ice melted, sea level rose again, flooding coastal areas and creating new coastlines. The ocean has witnessed the rise and fall of countless species. It has been home to trilobites, ammonites, ancient sharks, marine reptiles, and countless others. Some of these lineages have gone extinct. Others have evolved into the creatures we see today. The ocean is a museum of life, a place where evolution has been unfolding for more than 3 billion years. Waves are just energy passing through water. When you watch a wave, it looks like the water is moving forward, but mostly it is not. The water molecules move in small circles, up and down and forward and back, returning close to where they started. It is the energy that moves forward, travelling across the surface until it reaches the shore where it is finally released. Waves are created by wind. The stronger the wind, the longer it blows, and the greater the distance it blows over, called the fetch, the larger the waves become. In the open ocean, waves from different storms can overlap, creating complex patterns. Some waves travel thousands of miles from their point of origin, crossing entire ocean basins before reaching a distant shore. When waves approach the shore, they begin to interact with the seafloor. The bottom of the wave drags on the sand or rock, slowing it down, while the top continues forward. Eventually, the wave becomes too steep and breaks, releasing its energy onto the beach. This breaking is not violent or angry. It is simply energy finding its release. Tides keep time without clocks. They do not need batteries or winding. They are driven by the steady pull of the moon, which itself is locked in orbit around the Earth. The moon's orbit is slow and predictable, and so are the tides. For as long as the moon orbits the Earth, the tides will continue. Even in the quietest parts of the ocean, far from shore, far from storms, there is motion. Deep currents creep along the seafloor. Plankton drift with the slow circulation. Heat diffuses through the water, molecule by molecule. The ocean is never frozen in place. It is always adjusting, always responding to the subtle forces acting on it. The ocean has been moving for billions of years. It has circulated through ice ages and warm periods, through extinctions and explosions of life, through the slow drift of continents and the reshaping of the Earth's surface. It has been patient through all of it, neither rushed nor delayed, simply moving at its own pace. Tonight, you do not need to carry thoughts. You do not need to remember every fact, understand every process, or hold on to every detail. The ocean carries motion for the whole planet. It moves heat, water, nutrients, and life. And it does so without effort, without strain, without needing to think about it. It simply is. Your body too knows how to move without thinking. Your heart beats, your lungs breathe, your blood circulates. These are rhythms you do not control, and you do not need to. They happen on their own, just as the ocean's currents flow on their own, just as the tides rise and fall on their own. Sleep is your body's way of doing the same thing the ocean does, restoring, resetting, and letting the next gentle moment arrive. You do not have to force it. You do not have to worry about it. You simply let go and let the natural rhythms take over. Just one more small fact, and then we drift. The ocean is still out there, moving in the dark. Tides are shifting. Currents are flowing. Waves are travelling across open water. Plankton are drifting. Deep-sea creatures are gliding through the black. The ocean is doing what it has always done, and it will continue to do so long after this night has passed. You are safe. You are still. You are supported like water floating on denser water, like a surface layer warmed by the sun. You do not need to hold yourself up. You can let the world carry you, just as the ocean carries everything within it. Breathe slowly like the tide coming in. Hold for a moment, like the high water resting at the shore. Breathe out, like the tide retreating. Hold for a moment, like the stillness between breaths, And again. In, hold, out, hold. Slow and steady, no effort, just the natural rhythm of air moving in and out of your body. The ocean does not hurry. It has no deadlines, no appointments, no urgency. It simply is, and it moves in its own time. You can do the same. There is nowhere you need to be, nothing you need to do, no thought you need to hold. The ocean has been moving for billions of years, and sleep is your body's way of joining that rhythm, restoring, resetting, and letting the next gentle moment arrive. Just one more small fact, and then we drift. The ocean is patience itself. It shapes coastlines one grain of sand at a time. It wears down cliffs over millennia. It carries sediment from one side of the planet to the other, slowly, grain by grain. There is no rush. There is only the steady, unending motion. And you tonight can be just as patient with yourself. You do not need to fall asleep quickly. You do not need to force anything. You can simply rest, breathe, and let the gentle facts settle in your mind like sediment drifting to the seafloor. Some will stay, some will dissolve. It does not matter. What matters is the calm, the stillness, the quiet sense that everything is moving as it should. The ocean holds the planet, and tonight you can let go knowing that the world will keep turning, the tides will keep shifting, and the gentle rhythms of water and air and life will continue steady and sure while you rest. Just one more small fact, and then we drift. The next story is about to begin. Please relax and enjoy.